all, though, what I'd like to do is kind of give you an overview of what Isabelle UTP is and what we hope it can be used for. And indeed, that's basically what this tutorial is all about. It's all about how we can, what UTP is, what we can do with it. And by the way, just to remind you, if you are feeling thirsty, there are some cups there and there's a chilled water tap outside. So feel free to go there. We'll probably take a short break later. Okay, so integrated formal methods with Isabelle UTP. So the agenda for today, we're going to look at functional programming with Isabelle Whole. We're going to look at how we can do imperative programming with Isabelle UTP, and assuming we get that far, we're going to look at reactive programming with Isabelle UTP. So Isabelle UTP can be applied to all kinds of different languages. So not just imperative languages, but also languages with concurrency, languages with real-time, languages with pointers, all kinds of different things. As I said, what we're trying to aim for is a platform for integration of formal methods by unifying semantics. But first, some context. So we've talked a lot about assurance, haven't we, this week? We talked a lot about assurance cases and their importance in safety processes. And I think we all know what assurance cases are, and we all know what CyPhyAssure is by now, so I'm going to skip that over. So if we think of the use of analysis with formal methods, and we think about algorithms and different codes, we have to think, what do we need in order to be able to analyze a program like this? So this is insertion sort in C. So if I want to be able to verify this program, how do I do that? What do I need? What are the essential elements I need to be able to do formal methods? That's a question. Jakub? Yes, you do. You would need an invariant. Yes.
I need also some reasoning.
Yeah. Yeah. So there's a lot of different components that we need actually, but fundamentally, we're going to need a formal model, so formal semantics, as Jakub said, that captures the program's behavioral semantics. So we're going to need to model this program somehow as a mathematical object so that we can then manipulate it using mathematics, ask questions of it, and hopefully verify properties of it. And then the second thing that we need is analysis techniques, a variety of analysis techniques, right? So I guess we've heard of things like Hoare logic and separation logic, refinement calculus. These are all approaches people have developed to analysis and stepwise development of computer programs. And Isabelle UTP claims to be, and UTP claims to be able to capture a wide variety of formal models and analysis techniques. And of course, we have to make sure that if we're using these in assurance, as we've said, the models have an appropriate level of abstraction and can be linked to real-world artifacts. And we've said a lot about that and how we think about doing that in terms of validation, and I'm not going to say much more about that today. So we're just assuming, okay, formal methods are somehow useful, but how do we apply them and how do we build tools for them? We saw this before, this definition. So this is what DO333, the DO178C formal method supplement says. A formal model, what's a formal method? Well, it's a formal model combined with a formal analysis technique. We spoke about the formality spectrum already. Sorry, I'm reusing some of my slides. So let's now think a little bit more about integrated formal methods and unifying theories. So if we think about verification of cyber-physical systems, as we've talked a lot about, we have to integrate together a wide variety of notations, right? So if we think about something like an autonomous robot or something like that, we're going to have to bring together things like differential equations, control laws in languages like Simulink and Modelica, We may have some kind of state machine, as Anna did, right, to represent the behavior of the robotic controller. We're going to need, obviously, program code there as well, so C code, C++, all kinds of things, although, yeah, we don't advocate the use of C, but it is, of course, being used by a lot of people, and so somehow we need to be able to think about how we're going to deal with that. And then, of course, we have real people, so all variety of things that we need to model. And somehow we need to be able to integrate these different models together. We need to be able to have a unified view of our system models so that we can, of course, do holistic verification. So we can't just make do with verifying each of these things in isolation because they might have very different meanings. What we need to be able to do is integrate them somehow. So here's an example. This is just to kind of try and motivate this a little bit. So this is this small autonomous robot that I talked about earlier in the week, called TUG, which is a hospital material transportation robot from the US. It travels around the corridor, and it collects things and moves them from place to place. And it does this by using infrared sensors to build a kind of picture of its environment, and it has a map inside of it that it can use to do localization. So for this robot, if we want to be able to verify it, so there's a very good paper about verification of robots in Chimera, which this diagram is taken from. And that paper shows how we can model a robot geometrically, how we can model it in terms of its current trajectory. So this is the robot here. It's moving along this kind of curve. It has a velocity. It has a current position. And we can somehow use this kind of geometric model to think about the robot in its environment. So that's one aspect of things. But another aspect is the actual localization algorithm itself, so RANSAC. So random sample consensus is an algorithm that sensor readings are very noisy. Infrared sensor readings are very noisy, and so as the robot's traveling along, it's taking these sensor readings, but some of them are going to be outliers. Some of them are just going to be noise that it needs to filter out, and RANSAC is an algorithm that allows you to do that. So ultimately, you're looking for a line, right? In a very basic scenario where you've just got a wall on either side of you, you want to be able to see, well, where is that line? So you want to be able to filter out the points that are not relevant. And so RANSAC is an algorithm that allows you to do that. But this algorithm is actually quite complex because it's probabilistic in nature. It employs reasoning using the normal distribution, and because it has pseudo-random number generators. So because of that, in order to verify this kind of robot, we need to be able to think about both these kinds of models. Right? So we need integrated formal methods. Yeah, I went through these quotes as well earlier in the week, but just to draw your attention particularly to this last one. So the 1990s, there were lots of people talking about integrated formal methods. You know, how can we bring together these different notations and use them together? And not just from a notational aspect, but from a methodological aspect. So Manfred Breuer, for instance, he wrote a very good paper, which unfortunately isn't on here, but that was about how to integrate formal methods into traditional software engineering processes. So there were lots of people thinking about this question in all of its different aspects. And one of the, yes? Yes. So the full background to the history of integrated formal methods is in the survey paper that we sent out, and also, of course, Mary and Matt's paper that they did the session on earlier in the week. Now, out of all this discussion about integrated formal methods, Tony Hoare and He Jifeng toward the end of the 1990s wrote a book called Unifying Theories of Programming. And they were looking at this question of how do we unify all these different languages and notations. And what they said was, so they were really thinking about analysis tools, but methods as well, but mainly the different tools. And what they said is that to ensure that these different analysis tools may be safely used in combination, it's essential that their underlying theories be unified. right? And this was kind of a general theme of everyone who was looking at this. If you want to do integrated formal methods, you need unifying semantics. And this is what unifying theories of programming is all about. It's about how do we take all of these different notations and have a unifying view on them so that we can treat them as mathematical objects, but also relate them to one another to understand how they fit together so that we can do this kind of multifarious verification. And I've already showed this. So then the challenge of unification, how do we classify and relate all these different languages? Are there core principles that unify them? And it turns out, yes, there are, of course. We're familiar with programming language paradigms, aren't we? We can think of things like functional, concurrent, object-oriented, mobile, real-time, and hybrid. How do we integrate and link their various formal semantics? Can we use the tools together for analysis of autonomous robot models? And if we can, the payoff, of course, is modular construction of correct program analysis tools. So the idea of UTP is that once you can identify the fundamental paradigms that underlie your programming languages, they're called computational paradigms in UTP, we can use those computational paradigms as building blocks that will allow us to construct verification tools for a variety of notations. So yes, the UTP, created by Tony Hoare and He Jifeng. I guess we're all familiar with Tony Hoare, but you might not have heard of He Jifeng. But he is a very famous professor who is now in Shanghai, East China Normal University. And they together in Oxford came up with the unifying theories of programming. So it's a framework for heterogeneous formal semantics, as I've said. So let's think through this. Unifying, well, we need different ways of integrating different heterogeneous languages and notations. Theories, we're going to do this by formalizing the computational paradigms that underpin various notations. And programming. Initially, they were thinking at notations that can be executed by a computer, right? So they're not only, so sometimes this can confuse people because, well, we're not only thinking about programming, we're also thinking about modeling, aren't we? And modeling languages can't always, sometimes you have non-determinism, and sometimes it's not quite the right question to ask, can they be executed? But what I want to say is that unifying theories of programming can be applied to a wide variety of modeling languages as well. So once we've got this, so this is kind of the vision of unifying theories of programming. So at the bottom, you've got unifying theories of programming. Then on top of this, we build these building blocks, these semantic building blocks that will, these computational paradigms. We try to characterize them. What does it mean for a language to be object-oriented? What does it mean for a language to be concurrent? What does it mean for a language to be real-time? What is the core ideas of that paradigm? And how can we characterize the way that we observe programs using these kinds of paradigms? I'll explain more about how we characterize these building blocks as we go on. But once you've characterized those building blocks, then what you can do is you can start to construct semantic models. So UTP fundamentally is based on denotational semantics, so mathematical semantics where we associate mathematical objects with our programs, with our models, and so on. But it doesn't stop with denotational semantics, because really, of course, the purpose of having denotational semantics is to think about other kinds of semantics. So we have, of course, I guess most of us are familiar with operational semantics, right? Very important for being able to represent things like simulators and compilers and so on. So you have some kind of step relation, you know, you're explaining how do we step this program forward in time. But then you also have algebraic semantics, and algebraic semantics allows us to explain when two programs are equivalent using a set of equations, right? And perhaps most importantly, when thinking about automated verification, we have axiomatic semantics. And axiomatic semantics involve things like Hoare logic, separation logic, refinement calculus, rely guarantee. So these are all axiomatic semantics, right? They're all things that you can use deductively to reason about your program. And once you have, and then the idea of UTP is once you have created your different semantic models, so you first of all created your building block theories, you then integrate those building block theories to produce denotational semantics and other kinds of semantic models as well. And then you use those semantic models to build automated verification tools for a variety of different paradigms, or to link together existing tools at the semantic level. So UTP tries to sort of provide a way of understanding fundamentally what is my language from a computational standpoint. And then the idea is that this then allows us to organize all of these different notations together, to understand the links between them, so that we can then do these kind of heterogeneous verifications. Any questions so far before I move on? Okay. So let's look at the technology then. So we've talked. So that's kind of a potted overview of what Isabelle what UTP is about. It's worth saying that since Tony Hoare and Hedger Fung wrote their book back in 1998, there was a conference series that started, I think, in 2004, something like that. And the aim of this conference series, of course, UTP, was to look at developing different computational paradigms. So in their original UTP book, they looked at primarily at concurrency and state-based imperative programming and how these two things can be unified, and some other computational paradigms as well. But of course, we know there's much more than that. So all these other building blocks, the UTP theories have been developed for these different paradigms over the past 20 years since the UTP book was written. So for instance, we do have UTP theories for object orientation, we have UTP theories for real time, we have UTP theories for mobility, for probability, for hybrid systems as well, so which is what some of my work is about. So the claim is that UTP really can be used to characterize all of these different kinds of semantic models. But now let's look at the technology in a little bit more detail. So Isabelle, of course, we've heard a lot about, and we've heard about how, though it's well known for being a generic proof assistant, it provides a lot more than simply a theorem prover. It gives us a machine check document model with an extensible parser. It allows us to characterize lots of different kinds of grammars using different domains for different domain-specific languages. And this is one of the things I think that makes Isabelle such a powerful platform, because we can embed within it the syntax of a variety of different notations and languages so that you can compose them together. Of course, we need to be able to give semantics to those things, but Isabelle nevertheless gives us the presentation layer. So Burkhard Wolf yesterday was showing me a very nice C parser that he's integrated into Isabelle with syntax highlighting and everything, so that you can really see your code and reason about it. As we saw as well, Isabelle allows us to support both formal and informal content, semi-formal notations, and so on. So it doesn't force you to give a formal semantics for everything that you've got. But obviously, if you do have one, there's more you're going to be able to do. And Isabelle is also highly extensible. It allows plugins that interface with external tools like automated theorem provers, SMT solvers, and so on. I'll see if I'll... So yes, it's the Eclipse for integrated formal methods, or mathematics indeed. Since Isabelle allows you to ultimately describe most things that you would expect to be able to describe in mathematics. So for instance, for hybrid systems, the example that Burkhard Wolf was showing, some brave person called John Harrison built an entire stack for analysis. Right? And you can imagine what you need to do that. So first of all, you need to be able to describe topology. And on top of topology, you need to describe things like limits. You need metric spaces. You need real numbers, Cauchy sequences. Then you need to start to talk about differentiability. And then from that, you can start to describe ordinary differential equations and so on. And then finally, from all that infrastructure, you can then start to do reasoning about hybrid systems. There's been similar developments for probability. Essentially, this is all mechanization of textbook mathematics, right? So one of the ideas with Isabelle is that you have your mathematical textbook, and you can take the theories that are in there, all the definitions and theorems, and reproduce them in the tool, but then put them to work for doing all kinds of different reasoning. So it's a very powerful tool. And here's an overview of the architecture of Isabelle. So we have, so essentially the way that this works is, so Isabelle JEdit that you've been interacting with is the front end for Isabelle. So you type things into Isabelle, and it sends those edits to the Isabelle backend. It executes those edits within something called the using a meta language called P.ML, Isabelle ML really. And then it sends you back markup. So as you're editing, Isabelle is taking those edits, trying to work out what those edits mean, and inform you of what they mean. So it's asynchronous proof processing, so you can actually see the output of Isabelle as you're typing. And within Isabelle itself, there's a variety of different facilities. I'm not going to go through all of these, but you can describe new commands. So you can describe things like data types, records. You've got proof tactics, simp, auto. You've got first-order theorem provers in there. And you have a proof kernel that gives you things like types and terms, theorems and theories, which Burkhardt made use of. And as well, you have integrators. And one of the most famous integrators is a tool called Sledgehammer. And Sledgehammer allows you to make use of external automated reasoning tools. So things like the Z3 SMT solver, CVC4, Vampire, eSpace, a variety of automated first-order theorem provers that we can make use of within Isabelle. And Sledgehammer, in many ways, is why I became so excited about Isabelle, because before Sledgehammer, proof was very manual. You had to literally go through and do your logical deduction step by step. But following on from the arrival of Sledgehammer, now you could, if you didn't know what to do in a proof goal, you just type Sledgehammer, and it sends off your proof goal to these external automated theorem provers and gives you back the results. Right? It makes proving things much, much easier. So all of this together then makes Isabelle a very powerful platform. So one other thing I want to say, it also has code generation facilities. So if you can use it to verify program code, then you can generate code for a variety of languages in that, and then you have somehow certified code that you can execute. Okay, so I think I am going to skip over some more of these technical details because I'd like us to get into using Isabelle. Just a few things to say. So Isabelle Hol is fundamentally a functional programming language at its core. It's based on things like lambda calculus. It is first-order parametrically polymorphic, so you have things like parametric types in there. The type system is similar to something like Haskell or ML, but a little bit more restricted. It allows you to type things in Unicode, so you have these kind of markup codes that we'll see in a minute, which allow you to write things so they end up looking mathematical in the editor. So it provides you with all those kinds of things. So fundamentally, Isabelle Hol is founded upon an axiomatic type set theory with about 15 axioms. Now, one of the key things about Isabelle is it follows this architecture called LCF, where the only individual who can produce certified theorems is the proof kernel, right? So you can't just produce theorems. You can't just say, well, I say this is true. You're not allowed to do that. Only the proof kernel is allowed to do that. And the way that the proof kernel does that is by making use of axioms. Of course, we need axioms. We need to be able to axiomatize our mathematics. And so Hol is founded upon a set theory with 15 axioms. And from basically all the theories that are built within Isabelle ultimately are all in terms of these 15 axioms. And I just want you to absorb that for a little bit. So when you do calculus in Isabelle, ultimately everything could, if you wanted to, be boiled down into set theory. Right? And that's how mathematics works, right? You know, everything ultimately is set theory, and Isabelle is really implementing that idea, right? I think it's very impressive. So it gives us a functional specification language with things like data types, recursive functions, and so on. And there's loads of formalized mathematics. I've mentioned about the archive of formal proofs, but I think that's enough. So now let's get into some exercises. I ought to mention that the exercises here are based on a very nice tutorial by Tobias Nipko, who's one of the original developers of Isabelle Hall, called Programming Improving in Isabelle Hall. And if you'd like to learn more about the foundations of Isabelle Hall, I would really encourage you to look at that tutorial in more detail. So this is the Isabelle interface. So as Boo said, if you were here yesterday, every Isabelle so Isabelle is a collection of theories, a collection of theory files, and these theory files create definitions and proofs and so on, and you can import one theory from another. And if you import one theory from another, that means that all of the definitions and proofs which you declared there will come into scope. Right. So what we're doing in here is we say, so first of all, this section command at the top, this has no actual formal meaning to it at all. This is just markup. This is because Isabelle has a document preparation engine, so I can take this document, run it through that, and it will give me a PDF output that will be equivalent to this. And so this is just kind of marking up things in there, saying, okay, so this should just be a paragraph of text or something like that. So this is this kind of mix of informal and formal content within in Isabelle theory. But then we're going to load up a theory context, Isabelle Fun, and this is going to import main. Right, and main is whole, basically. So it's all of the libraries that are available in the whole logic. And this includes things like a functional list, natural numbers, rational numbers, complete lattices. There's quite a large library of algebraic theory there. But we're not going to make use of a lot of that today. What we're going to do now is create some very simple data types and some functions for those data types. So we're going to basically do some functional programming. So first of all, I'm creating a data type for natural numbers. Now, just to show you the kind of features of Isabelle, so if you make a mistake, Isabelle will complain. One of the things that you need to do in order to see the content of the error, so at the bottom here we have an output, a number of different tabs. So we have output, we have Sledgehammer that we'll see in a minute that gives us access to these automated theorem provers. And then we have the output pane. Now, by default, Isabelle will not have this box checked, proof state. So if you look on your installation of Isabelle, you'll find that that box isn't checked. And I encourage you to check that box, because without that box being checked, you're not going to be able to see what the content of the output from these commands is. Right. It's telling me command expected, but identified type was found. So I'm going to correct that. Okay, so we've created an algebraic data type for natural numbers. Of course, natural numbers can be constructed in terms of zeros and successors. Right, I guess we all know that. And then what I can do is I create a recursive function called add, which is going to add together two natural numbers. This is not going to be surprising, I suppose. So if we want to add a 0 and a net, then this is equal to n. And if we want to add a successor, then what we're going to need is we're going to need to pull that successor out and recursively call add. Right. So fun creates a recursive function. The name of the function we're creating is add, and we're going to give it type natural to natural to natural. Now, one of the things that can confuse people when they're using Isabelle for the first time is these quotation marks that you see all over the place. So Isabelle has kind of two levels of syntax. It has outer syntax and it has inner syntax. So the outer syntax is essentially the syntax of commands. So you have things like data type, subsection, fun, value. All of these are outer syntax. So these are commands that I'm manipulating the proof state. So when I type one of these commands, it is making an update to the internal state of Isabelle. Right, so once this data type command is executed, we now have a type available called NT that we can make use of. So that's outer syntax. But then we also have inner syntax, and inner syntax is the syntax of terms. So that's why we have the quotation marks. So here, for instance, so this is an equation, so this is a term, so this is inner syntax. And similarly here, we have another equation, right? You'll get used to it as you go along. Jeremy? Yes, of course. So there's a few different ways of adding comments. Probably the easiest way for you is to do these kinds of brackets, asterisk brackets. Yes. So, yes. Because this is an inductive data type, right? So it's either zero. So a natural number is either a 0 or the successor of a natural number, right? So it's this kind of inductive way of describing positive numbers. So, yes.
Is it the same as an algebraic type?
Yes, exactly. Yes.
So that is defined already. Standard library.
Yes. So successors. So there is indeed a type of natural numbers already defined. So if I write here, for instance, tip nat, then it's okay. It says yes, this type exists. What I can actually then do is, so Isabelle has got this quite nice hyperlink feature. So anything that I use within a term or an outer syntax command, I can control click. So if you hold down control and click on something, Isabelle will take you to where that thing was defined, right? So in this case, it's taken me to a location in the standard library, src hol, and the thing is called nat.thy, right? But we're don't worry about type defs. We're not going to go there because they're a little bit more tricky. But yes, there are different ways of defining data types in Isabelle Hol. The one that we're going to explore right now is the data type command. But, yes. Yes, sorry. No. Sorry, I misunderstood. So exactly. So what's actually happening here is it's actually quite involved when you create a data type because there's a number of different entities which are being created at the same time, right? So exactly as Mario said, so this is just like Bacchus now form, right? So the first of these atoms is a constructor. So we're creating a constructor called Z, which takes no parameters, right? And then we're creating a constructor called S, which takes one parameter, which is type NT. Now I could add more parameters if I wanted to, so I could do something strange like that. But once you have run this command, now we have available to us a number of different constants that we can make use of. So for instance, I have a command term, and term will allow me to ask what the type of a particular term is. So if I type term Z, it's going to tell me at the bottom here that Z is of type NT. By the way, is the text big enough for everybody, or would you like it to be bigger? Everyone happy with the text? Good. Cool. And the same for S. If I ask what's the type of S, well, it's a function, a total function from NT to NT, right? Because if I want to be able to construct a natural number, it can either be 0, which is just a natural already, or I have to give this an existing natural number. So for instance, I can build things like S of Z, and S of Z, and so on, right? So these are just functions, really, that are being created by the data type. Is that all clear? So one other thing so Isabelle is not simply a functional programming language, of course, it's a theorem prover. So actually in the background, you've got a load of other stuff going on as well. And just to give you an idea of this. If I use the print theorems command, this gives me a big long list of theorems that the data type command generated for me. Right, so these theorems are things that I'm going to be able to make use of in proofs. Now, Isabelle is set up so that I don't need to actually know about these theorems, so don't worry, you're not going to need to go through this list of things and work out what they all mean. I just want to say that the data type command is quite sophisticated, right, in terms of what's actually going on in the background. But we're going to ignore that for now. But yeah, just it's quite a helpful command, print theorems, because it will tell you the theorems that a particular command has produced. So similarly, so for this thing add, so we're creating a constant called add, which is a recursive function. And again, down here I can ask about add, and add is a function from natural to natural to natural. Okay. All right. So then we can also now evaluate this, right? So term only allows us to check whether a term is a valid term or not. So for instance, if I try and write in here something like this, sz, then it's going to give me a funny error. Why can't I add together s and z? Can anyone tell me what's wrong with what I've written there? No, so potentially. So if we add some brackets around here, we will get a well-typed term. I mean, I mistyped, right? So it's not clear what I mean. But here, for instance, if we say add of sz, then so this has now taken the one of the two parameters. So add takes two arguments, and now I've given it one, so I just get a function from natural to natural. Yes, it's a part, exactly, so that's the correct term for functional programming. This is a partially applied function, exactly. And that's exactly what's happening here as well, actually. So if I drop the brackets, of course, s, what is s? S is a function from type natural to natural. So if I try and give s as the first argument of add, then it's going to get a type mismatch, right? Because this is expecting a natural, but what I've given it is a function from natural to natural, right? So a way of fixing this is actually, I've really got to stop touching that keyboard. A way of fixing this is to do that. So I actually meant I wanted to add s, z, and z together. So that's good for term checking, but we also want to be able to evaluate these things. And so Isabelle has a function called value, and value is going to allow us to execute these functions, right? So what are we really doing here? We're adding together 2 and 1, right? So this is the natural number representation of 2, s, s, z, and this is the natural number representation of 1, right, s, z. So basically, this is 0 plus 1, this is 0 plus 1 plus 1. Right. And now what I can start to do is, so we now come on to what Isabelle's really good for, which is proving theorems. Right. So now that we have defined our function, it would be great if we could prove some properties about them. So let's first of all prove a slightly simpler property. So lemma add 1, we'll call it, add z m equals m. Right, so what am I saying here? I'm saying that if I add a 0 to a natural number m, then of course what I get is m, right? This is all very basic mathematical properties. Now Isabelle actually tells me, oh, so this is a theorem that I'm trying to prove. And Isabelle tells me, well, actually, this is already proved, and it gives me the theorem. And why was it already proved? Well, this was one of my 2 definitional equations for the add function, right? So we already said in the definition that add of 0 to a natural is a natural, right? So Isabelle already knows about that. So actually, I don't need to prove this. It already exists, but just so that we can prove it, we can say by simp. Yes, Shakub? exactly, which is exactly what we're doing here, right? So that was an easy one to prove. But what about the other way round? Sorry. So simp is one of Isabelle's proof tactics. It's called the simplifier. And so what the simplifier does is it applies simplification laws automatically. So each of these two equations is a simplification equation, right? So I can apply them from left to right to simplify something like this, right? So if I apply the simplifier to this, then it's going to say, well, what have we got here? So it doesn't match with that, but it does match with that. Okay, so we've got successor of something. So then I need to rewrite it to S of add of SZ, SZ, and then what have we got? Well, we've got something of this form again, and so on, until eventually you kind of do this expansion until you've got the value that you want, right? So simplifier is just applying all of these kinds of simplification laws. There are other ways of proving it. So for instance, one thing I could do, I could call sledgehammer at this point, which I do here. So in general, if you don't know what to do in Isabelle, which for me is a lot of the time, you can just hit this button, sledgehammer, and this is calling external automated theorem provers. Now in this case, because it's such a trivial thing, it just comes back with exactly what we had already. And what you can do is you can click on that, and then it's proved it. So sledgehammer was just set up automatically, so you don't have to set it up.
Mine is kind of having a timer problem with vampire and CPC4.
Yeah, so sometimes things will time out, but don't worry about that too much. So long as one of them is.
I don't have to do anything for the setup.
Well, so vampire is so there's an issue with so vampire has got a commercial license associated with it, but I just don't worry about it. It's fine. Enough of the theorem provers will work for this tutorial. We can talk about that more later if you want to. Okay, so then for a slightly more complicated one, if we want to have it the other way round, so that add of a natural number to 0 is the same natural number, Isabelle doesn't know this automatically, and so it's not given us this suggestion. And the reason for that is because actually we need to be able to do a proof by induction, right? And that's what we're doing here. So we're applying two proof tactics here. And so let's look at what happens. So if I go to output, and then I say apply induction, and induction, I'm hoping that we all know a little bit about induction. The inductive hypothesis then splits this into two possibilities. So first of all, I have to show that add 0 to 0 is 0, and that's trivial to prove. We proved that already, or something more general than that already. And then you have the inductive case, which is if I know that add m of 0 is m, then I also know that add suc of m 0 is s of m. Right. So that's a proof by induction. Now both of these cases can be discharged relatively painlessly, and that is done by a tactic called auto. Auto is like simp, but it also does automated deduction internally, so it's a bit more sophisticated. So basically, the take-home message is that really for most of the proofs that we're going to do, you only need to know three things. First of all, you need to know about induction. Secondly, you need to know about auto. Third, you need to know about sledgehammer. For most of the proofs that we're going to do here, that's all that we're going to need to use. It's going to be different when we come to imperative programs, but for functional programs, that's going to get you most of the way. So long as you can figure out the right variable to induct on and apply sledgehammer or auto in the right way, then it will work. Yes, Mario?
If you apply auto, it automatically discharges all those listing steps.
Yes, sorry, so yes, so simp and auto are different in that respect because simp will only apply to the first sub-goal which you've got in your list, whereas auto applies to all sub-goals simultaneously. Well, not simultaneously, in sequence, but yeah, so auto is quite powerful for that reason. Okay, so now what I'd like you to do is to do a couple of exercises, please. So I've told you about induction, I've told you about auto, I've told you about sledgehammer. Those tools are enough to be able to do these two exercises. You can just copy and complete, basically. You've got the basic principles that you need. So, yeah, let's see if we can do that. Yes? Yes. That's just the normal syntax highlighting. So red is good. In Isabelle, for some reason, red is good, pink is bad. Oh dear. Ask Macarius. Do you know the reason, Jakub? Okay. So there we go. So three exercises. So you've worked out, you've seen how as well to define recursive functions. So I'd also like you to complete this definition of multiplication, and and then there's some exercise after that as well. So let's do all these 5 exercises. And if you'd like to get... All right, so let's look at the answers to these exercises. So first of all, I guess you got for this one, this is quite straightforward. I'm just going to apply induction, and then auto, and then we're done. Commutativity will be similar. Now, in terms of the definition of completing the definition of multiplication, so we've already got the equation there that if we multiply 0 by a natural, then of course we get 0. And the case that we need is, of course, when we have successor of a natural and a natural. And then what's this going to be? Anyone? Yeah, that's right. So it's actually written on the board over there. So we're going to add n, and then we're going to do the multiplication of m and n. Right. And then we want to try and form a goal that multiplication is commutative, which is going to be m mult mn equals mult nm. Now what's happened? So we've got the first goal, which I think, so if we apply auto, I think our goals aren't going to reduce, because we also need to know that 0 has a right unit. So let's prove that one first. So sorry, that 0 is not a right unit, a right annihilator. Mult m z equals z. That one goes through. That's good. Now, in order for us to do this one, the easiest way actually is to call sledgehammer. So if we call sledgehammer on this goal, then what sledgehammer is going to tell us is it's going to tell us, okay, so I know how to do that. So I have a fact called mult right 0 that I can make use of. So if I add that to the simplifier, then it can do it. And then for the second one, we need another property. And it's at this point when I'm regretting not having answers. So I think it's probably actually just this property that we need to be able to prove actually. So if we take that, turn that into a lemma, Or maybe not. Well, let's think about this. Of course, because we also need the inverse of this one, right? Because, yeah, what we want, I think what we want to be able to do is, yeah, so we want to be able to commute that second argument there. Which we can't because we're doing an inductive proof. All right, I'm sorry. I forgot to prepare answers for that, so I'm going to leave that one for now. But hopefully this gives you the idea. That would be provable if I had an answer, but I'm afraid I forgot to prepare that. But hopefully that gives you the idea of how we can define functions and how we can prove theorems about them. Now, what I was going to get you to do next is to define the factorial function and to evaluate some values. But I think I'm going to skip over that just for the sake of time. So the next thing that we're doing in this theory is creating the theory of inductive lists. So we have a data type, a list equals, so what is a functional list? Well, somehow it's analogous to a natural number. But the difference here is that we now have a parameter. So this is a parametric type. So in Isabelle, when you have this kind of marker here, this prime, it means that we have a type variable here. So this is a variable which can be instantiated with any type. So like in Haskell and Z and so on. So we're here creating an A list, and the list can either be an empty list, or it can be an element A followed by a list, right? And I guess, so this is the sort of classic definition of a functional list. And then what we're going to do is we're going to define a function that allows us to append two lists. This is a cons, it just means construct or something like that. So it's just we add an element onto the front of a list. It's a constructor, so it's constructing a list by putting an element onto an existing list. So that then means that I can construct lists like this. So I can say cons of 1, cons of 2, cons of 3, nil. Right, for instance. So that's a list containing 3 elements, 1, 2, and 3. And then we have a concatenation function, which is defined in a similar way to the plus function. So this is a polymorphic function now because it can be applied to a list with any type parameter applied to it. We can also prove that so if I append an empty list to an empty list, then of course I'm just going to get the same list back, and the same is true the other way around, right? So append has got both a left and a right 0. Of course, unlike plus, append is not commutative, right? If I take a list and put another list on the end, that's not the same as putting them together in the other direction. I'm not going to get you to do these exercises because I think it would be painful for you. So let's just go through them one by one. So what we're proving here is that append is associative, which again we can just do by induction and auto. done. By the way, a slightly more concise way of writing this is using the by notation, which is how I often like to write things. So what we're saying here is, first of all, apply induction and then apply auto, and it's just a little bit more mathematically concise. Yes, that's right. So now what we're doing is we're proving this functional programming classic, which is to prove that if I reverse a list twice, I get the same list back. Right. So what I was going to ask you to do was to complete this definition. So the reverse of an empty list is, of course, an empty list. The reverse of a cons is what? So we have to append a single element onto the end. So we first of all take the remainder of the list and reverse it, and then we put this element on the end, right? And that then is how we can reverse it. So how the way that we write this is like this. So we write app reverse x's. So that does that reverse the remainder of the list, and then we're going to put a singleton list on the end, which looks like that, and that then gives us our definition of reverse. Yes?
Why did you have a functional declaration?
Here. So this is a polymorphic function, so I can apply it to a list containing any type. So this could be a list of naturals, it could be a list of real numbers, it could be a list of lists of things, or whatever.
So then, why in the reverse line cons x-axis, why don't you have a prime?
Where are we looking? Sorry? Up here.
No, just in the function reverse.
In the function reverse. Yes. So we've got the a prime, a prime. Yes. Yes.
And then the first time reverse avoid least all.
Mm-hmm.
And then you have reverse, you say cons x-xs.
Yes.
What is the type of it? There is no prime or...
We'll see. So
it's list of actually.
because they're in. So Isabelle does what's called type inference. So it can work out what the type of these two things is. So we already told it when we created the data type that a cons is effectively a function from A and A list to A list, right? And so then I don't have to repeat the type information here because it already knows that I've got an A list coming in. And so it can then use that definition to split this apart and infer, well, X then must match with this, and XS must match with A list. Right. Yes?
Just for clarification, so the prime in front of the prime,
Yeah.
is it syntactically
It's
necessary
yes.
to help Isabelle internally
Yes.
figuring out
Yes.
what to do?
Yes. So that is how you write a type parameter. So a type parameter is always written with a prime first to distinguish it from other kinds of constructors. All right, and then, so what we're going to do now is, just to finish off, we're going to prove that the reverse of an empty list, the reverse of the reverse of a list is the same list. Now, this is not going to work, but I know why in this occasion. So if we try to do induction excess and apply auto, well, we're going to have a residual proof goal left over. So in reality, we need another property, which I'm going to call reverse append. And what reverse append is going to tell us is that what the reverse of two appended lists means. Can anyone tell me what's the reverse of two appended lists? So if I take two lists, connect them together, and then reverse that, what am I going to? How can I rewrite that? Yes, exactly. So you're going to get append of reverse x's, sorry, other way round, of course, y's and x's, right? And this is a property that we can prove easily. Oops. Gone. And then if we add this to the simplifier, so you can also instruct auto to take advantage of other simplification rules. It goes through. We could, by the way, have just run sledgehammer at that point, and it would have given us the same thing. Okay, so that's the basics of Isabelle Hall. So that's to kind of give you an overview of what we can achieve with Isabelle Hall. So it's a functional programming language, so we can now do verification of functional programs using this. Of course, all the pain that we've just been through of kind of declaring all these data types and stuff has actually already been done for us. So, as was hinted earlier, we do already have natural numbers available, and actually we can write them in a much nicer way. So apologies, Jeremy, but you can just write down actually things like 5 plus 6 if you want to, and so on. So all of these kinds of syntactic extensions are all part of Hall. So you don't have to do all of this. This is just to kind of give you an idea of how we go about defining functions and proving things about them. So for instance, that property that we just proved, so rev is already there. So actually, yeah, we can go and look at that. So that's already defined in the standard library. And you'll see that we've actually got much nicer syntax that's been defined for it. So an empty list looks like this. A cons has got this kind of infix symbol associated with it, and append is likewise an infix at. And we can give much nicer syntax, these to make our DSLs much more appealing, much easier to work with. But fundamentally, underneath that, what we've just done, that's exactly how all of these things are defined and how they are proved. And there's a large library of such properties. So for instance, the reverse of an empty list, that's already proved actually, and Isabelle will refer us to that. Okay, so that's Isabelle Hall. That's the things that we can do with it. So what we're going to do now is turn our attention to Isabelle UTP, right? So we've looked at functional programs, but of course functional programs, well, that's one paradigm. It's a useful paradigm. I think probably most of us will agree with that. But there are other paradigms that we want to be able to use as well. Imperative programming, concurrent programming, and so on. How are we going to characterize these? And this is really what Isabelle UTP. Okay, so let's skip that over. So unifying theories of programming, let's go into a little bit more detail about it. So as I've said, one of the things about, so UTP is really trying to be a very holistic approach to characterizing these different computational paradigms. And this is a list that we came up with by looking through previous years of the UTP symposium, things that UTP has been used for. So it's been used for aspect-oriented design, event-driven programming, hybrid programming, object orientation, probabilistic programming, on and on it goes. So all kinds of people have been using UTP to try and characterize these different kinds of languages. So yes, it was a book in 1998, which is available online for free. So if you go to unifyingtheories.org, you don't have to go there now. But there's a link on the website. So there was something called the Verified Software Initiative as well, which set a long-term research agenda, which broadly speaking said this. So researchers have proposed programming theories, so different ways of thinking about languages in terms of mathematics. Practitioners have proposed, excuse me, practitioners have proposed pragmatic programming paradigms, nice P's. And how do we understand the relationship between all of these? So Rick Hayner, who some of you might have heard of, he's formerly a professor in Canada, and he wrote a very good paper called Retrospective and Prospective Unifying Theories, which kind of gives the history of how UTP came about. So UTP gives three principal ways to study different languages. So first of all, by computational paradigms, we've already mentioned about that. Secondly, by level of abstraction. So different languages have different abstractions, right? We can view them at a very high level where we're not observing too much, such as in like a modeling language like UML or something like that. But we can also go down to a very concrete level, right, where you've got machine code and so on. These are different levels of abstraction that we need to be able to consider. And finally, by different methods of presentation. So different semantic presentations include things like axiomatic semantics, operational semantics, and so on that we've already said. So computational paradigms. There are lots and lots of programming languages, numbered in the thousands. Peter Landin wrote a paper called The Next 700 Programming Languages. So there are general purpose languages like C++, Java, Scala, Python, Perl, on it goes. And as well domain-specific modeling languages like, not modeling languages, domain-specific programming languages, HTML, Verilog, Mathematica, SQL, to name a few. So how do we make sense of all of these languages? How do we think about the relationships between them? And one way to do that the UTP proposes is by considering these different computational paradigms. So identify the common concepts that are present in these languages and deal separately with additions and variations. So really trying to see where one idea is present in several languages and then trying to use those ideas to link the languages together. So two fundamental scientific principles used in UTP: simplicity of presentation and separation of concerns. So we want to be able to kind of boil these computational paradigms down to their most simplest form, and we want to separate out the separate concerns. So rather than looking at a big language like Scala in one go, try and think about the different paradigms that actually make that up. And Scala's an interesting language, right? If you've ever used it, it has functional programming. Of course, it has object-oriented programming. It has concurrency. It's a language that invokes lots of different kinds of paradigms, and UTP proposes that we should be able to separate these and consider them in isolation. Abstraction, we've already mentioned about. It's an orthogonal classification, so we, of course, have very high-level languages like requirements capture and analysis, working down to architectural descriptions, requirements, solutions, and then we have component definitions, contracts for interfaces for those components, and then going down into actual programming languages with a full behavioral description, and finally, platform-specific implementations, right? So all these different levels of abstraction. And UTP allows us to link these different levels using refinement. So a very important concept in UTP is the concept of refinement. So how do I say that one program is more abstract than another, or more refined than another? And the idea is to preserve correctness from requirements down to code. So in terms of presentation, we can classify the different language definitions in terms of different semantic models, of course. We've mentioned these, but just in a little bit more detail. Denotational semantics, of course, where you have each syntactic phrase of your language is given a mathematical denotation. And then the specification is just a set of possible denotations, right? And this gives us a simple correctness criterion, right? Because if we know that all of the syntactic constructs of our language, like assignment, sequential composition, parallel composition, and so on, can be boiled down into mathematical denotations, and I can also express my specification as a set of possible denotations, then of course you then have the ability to express the relationship between these using refinement. Algebraic semantics, we've already talked about. You're talking about equalities, right, between different elements of the language. So you might want to say something like sequential composition is associative. If I abort and then do something, well, it doesn't matter what I did because I aborted already. These kinds of equalities. And these kinds of semantics tend to be quite useful for engineers because they allow us to rewrite our programs in various ways. And finally, operational semantics. So axiomatic semantics actually ought to be in the list as well, but we mentioned about it already. So operational semantics then is about an abstract mathematical machine. You know, programs are defined by how they execute, the sequence of steps that you have to go through in executing them. So the UTP research agenda is to try and classify all the different programming languages in the world that exist, find the interesting computational paradigms that underlie them, try and determine what kind of level of abstraction you're dealing with, what kind of semantic models that you have associated with those languages, and then link them together in various ways. And the idea here is that we want to have a theory supermarket. You know, so when you're putting together your language, like a recipe, you shop for exactly the ingredients that you need to build that language, and then you can be confident that you can use your theories together to construct your semantic model and your verification tools. And this leads us to the concept of a UTP theory, which I think we're not going to be able to go into much detail in this tutorial, but essentially a UTP theory is one of these building block theories, one of these building block computational paradigms. And they're defined in terms of an alphabet. So the alphabet gives us the set of things that we can observe. So UTP is all about observation. Are you guys leaving? I'll just say bye-bye. Thank you for coming. A signature, so this is the set of operators that we use to construct our programs, and so things like sequential composition, assignment, and so on. And then finally, these things called healthiness conditions. And healthiness conditions are very important because they really explain the logical structure of our language. So we'll look more at this if we get there later in the lecture. But we're going to think now about fundamentals. And Jim Woodcock's just walked into the room, and these are his slides, so he should come and present them. No. I won't force him to do that. Yeah, so this is... So Jim and I have done this tutorial a few times, so it's a pleasure to be able to go through these slides myself. So fundamentals. So UTP is based on something called the alphabetized relational calculus. So ultimately in UTP, any kind of program that you're going to deal with is going to be represented as some kind of relation. Who here knows what I mean by a relation? Yeah. So I'm talking like in the Tarski sense here of a relation. So basically a specification that explains how a number of input variables are related to a number of output variables, right? So it's well known that we can characterize a program using one of these relations. And so then we have a number of different variables that we're going to use to observe the behavior of our program. So here's a few examples. So for instance, we might have a variable called OK, which is telling us, okay, is my program started successfully, or has it aborted? Is this a normal execution or not? You could have a variable tr, which indicates a trace, so the set of events that this program can engage in. You might have a variable called wait, which is telling me whether the program is waiting for interaction with the environment. So these are the kinds of things we want to observe about a program. Right, so what kind of state is the program in? And as well, what state is the world in? So UTP allows us to kind of grapple with this question of, in this kind of technical system where you have both some kind of model of the real world and also some kind of model of your digital system as in a cyber-physical system, what are the things that those two share, and how do they communicate with one another? And relations will allow us to specify these kinds of things. So a relation consists of an alphabet, which is the set of variables that the program is permitted to talk about. So you can't refer to any variables that are not in your alphabet, so that's a kind of fundamental. And we're going to write relations using these uppercase variables. And variables can be so if you've ever used Z notation, in Z notation, the way that we denote whether a variable is input or output or before or after is by either priming it or not, right? So for instance, if I want to say that after executing, the value of x should have increased, I could write that down by the predicate x primed is greater than x. Right, so this is a very simple specification. It tells us that the program variable x, after this program has executed, should have increased strictly. Right, and then you can conjoin these kind of clauses together to give the behavior of your different variables. So we can therefore split our variables into two parts, the input alphabet and the output alphabet. And if the input alphabet and the output alphabet is the same modulo priming, then we have a homogeneous relation. So if we have the same number, if we have the same input variables and the same output variables, which most of the time we do, but there are exceptions to that, then we have a homogeneous relation. Right? And most of the relationships we'll deal with will be homogeneous. We also have conditions. And conditions are going to be written using these lowercase letters. And these are relations that do not talk about output variables. So for instance, if you're writing down an if statement, and you want to say if x is greater than 1, well, that x there is talking about the initial value of x, not the final value of x, right? So we could specify that using a condition. So this is very similar to Z schema calculus. And so yes, this kind of convention of priming and not priming variables is really fundamental. Now, Isabelle UTP is a mechanization of UTP, as I've said. So a way of thinking about these alphabets is as types, right? So the set of the set of variables that you wish to observe is somehow a type, right? It's the set of observations that a particular relation has associated with it. So in Isabelle UTP, we model alphabets using types, and particularly record types. So in the first half of the tutorial, I showed you algebraic data types, but Isabelle has a whole range of different types that you can declare, and it also has record types. And a very common way of modeling program memory in a computer program is using a record, right? Where each of your fields of your record corresponds to one of the variables of your program. And we use a similar convention here. By the way, to just slightly hint on your question earlier, Andre, so actually there's another layer on that, which is that each of those fields also has a lens associated with it. So variables in Isabelle UTP are modeled using something called lenses, which I'm not really going to go into because it's a little bit too theoretical. But it turns out that lenses basically allow us to give an algebraic semantics to program variables, which is a very useful thing to be able to do, but that's all I'm going to say about that. But consequently, in Isabelle UTP, these two concepts, relations and conditions, are denoted by these two types, which unhelpfully are written the other way around. So you have a type of predicate. So in this presentation, I use these kind of square brackets to denote that alpha here is a type variable. So in Isabelle, this is just written using the priming thing, but when I write this mathematically, I prefer to use this kind of notation because I think it's a little bit easier to read in mathematics. So basically what this is saying, so this is the type of predicates whose alphabet is alpha. And then similarly, we have one for relations, specifically homogeneous relations, and this is the type of relations which are homogeneous relations over the alphabet alpha. So as I said, fundamental to UTP is the concept of refinement. And refinement is essentially implication or reverse implication. So in order to define refinement, we first of all have to define this notion of universal closure. And what universal closure does is it universally quantifies all of the variables in my alphabet. So it's basically saying for all x, y, z, p, where p is the relation or the predicate that you're dealing with. And then we can define refinement like this. So here S is a specification, P is a program, although actually these could both be specifications. They don't have to denote programs, I just call them S and P sort of to hint at that. The point is that P is less abstract, it's more concrete. So refinement here goes from abstract to concrete in that direction. And so then we write that, we denote that like this. So P implies S. So every behavior that P can give us is a behavior of S, right? Which is, of course, what you want in a specification, right? So your specification will typically be non-deterministic. It will give you a whole load of possible behaviors, like this one, right? So that predicate that I wrote down over there, x primed equals x, there's a whole load of programs that could implement that. So in particular, it is the case that So x primed is greater than x is refined by assign 1 to x. Now, of course, assignment is doing lots of other things, but you get the idea. So once we have refinement, we can then write down specifications. So here's another specification, actually similar to what we had before, but here we've got two variables, and the specification here is saying that in the final state, x is greater than its initial value, and y stays the same, right? So that's how you can then specify the behavior of those two variables. And then a possible implementation of that, like the one I had over here, but where we've got the two variables, is x. So we're going to do a simultaneous assignment, and we're going to say x and y are assigned to x plus 1 and y respectively. So actually, we could just omit this. We could just omit the y and just write x equals x plus 1 as we did over there. We just got it explicitly written there. Now then, crucially, so UTP, so we're based on denotational semantics here. So each of our programming operators is ultimately going to be given a meaning as a relational predicate. So every operator that we have ultimately can be boiled down to one of these relations, right? And that's great because since we can embed programs into the language of predicates, of course, we now have a universal domain in which we can both do specification and implementation, right? Because programs are just deterministic relations, essentially. That means that we can just express the refinement in this way. Right, and this is just kind of showing an example of how you can ultimately boil this down. So this kind of refinement, that this implementation is refined by this specification, can actually be boiled down into an implication once we know the meaning of assignment, which we haven't quite got there. But essentially what assignment is saying is that x primed is going to take on the initial value of x plus 1 and y is going to stay the same. Well, of course, that implies our specification, right? So that gives us a specification, a general specification mechanism for relations. We also have other operators which we can make use of at this level. So I'm not going to touch too much on lattices, but it's worth noting that predicates, that relations form a complete lattice under refinement. And one of the results of that is that we can reason about non-determinism, we can reason about recursion, we can reason about induction, and all of these kinds of things. So I'll just tell you this operator. So this operator here basically represents a non-deterministic choice. And it can just be denoted by a disjunction as a predicate. So basically you're saying it could either be this behavior or it could be that behavior. So that's just a very simple programming operator that we have, a non-deterministic choice, and very useful for specification. I'll not go into this one, although this is just simply stating a duality result, that we also have the other, it's dual operator. But really the crucial thing here is that we have a link now between non-determinism and refinement. So what this result tells us is that refinement is really reduction of non-determinism, right? So what does this mean? So P is refined by Q if the non-deterministic choice of P and Q is in fact P. So what this is really telling us is that Q doesn't present any options that P didn't already present us with. And so you can specify that using a non-deterministic choice. So yes, as I said, we get a complete lattice, but I'll skip over those. We can express fixed points, and fixed points will allow us to write down inductive definitions. And basically, the way to think about a fixed point is it's just something that can be expanded. So if I write down something like mu of f, then that's really equal to f applied to mu of f, or f of f, and so on, right? So you can unroll f as many times as you like. We'll see an example of that in a moment. But yeah, so you have this kind of law for a fixed point operator, right? So this is the strongest fixed point operator, and this just tells us that nu of f is actually equal to f applied to nu of f, right? So that's what it means for this to be a fixed point, right? That if I apply f over and over again, then it doesn't actually have any effect. But it means basically, so this is kind of like an iteration. It's like I'm unfolding the body of my program. Yes? That's the answer. It's historic. You can present the lattice either way up. If you invert a complete lattice, you get a complete lattice, but that's not so concerning, I think. I think I'm going to skip over these because I don't want to go into too much detail about complete lattices. So what I want to do once we come back from lunch is go through this whole process of how we can think about denotational semantics, algebraic semantics, axiomatic semantics, and operational semantics, and how we can do those in Isabelle UTP. But just to give you a flavour of this, let me show you. Actually, no, I'm not going to show you. Because I think I need to compile the UTP, and I don't want to force you to wait for that. So we'll stop there for now. And so when we come back after lunch, I'll tell you a little bit more about this, and then we'll actually get into Isabelle UTP itself. We'll see how we can model programs using this kind of syntax and how we can prove results about them automatically. And hopefully that will be a little bit more intuitive than the first session. All right, so I'll stop there for now. We'll work through it. Now this is going to be very different to functional programming, because now we're in a more imperative setting. Now we're in a setting where we're going to be reasoning about things like state variables, we're going to be doing assignments, and so on and so on. But everything that you have learned so far about Isabelle Hall still applies. So as I said, this is a conservative extension of Hall. So we can still write functions, we can still prove things about functions, but we can also now write imperative programs in the traditional style. So let's go through this. So the first thing, so the way that Isabelle UTP works is, in order to verify a program, first of all, you have to come up with a state space for that program. So as I mentioned earlier, we kind of have this alphabets as types approach, right, where the set of variables that you want to have is going to be modeled by a record type, right? Now, actually, we've got our own command that allows us to create one of these alphabets, and you'll see it there, alphabet. So what this does is, it creates a new state space type, and that type is going to be called state. So this is a type like we created with data type, but it's a different kind of type. And we're going to create two variables, right? X of type nat and Y of type nat. Okay? Now, we're going to create a very, very basic program in order to reason about. And this is the program here, and I'm just going to take a couple of minutes just to explain what's going on. So basic prog, so abbreviation. So this is kind of like fun that we saw in the previous session, but we're not creating a recursive function now. We're doing something much simpler. We're simply creating a new constant called basic underscore prog, which is going to be a function from nat to state hrel. So effectively what this is a constructor for a program, right? So we mentioned before lunch that the way that we model programs is using relations, and we have a type for homogeneous relations which is called HREL. And so you can really read this as like prog. So it's a program over this state space. So it's a program that manipulates only the variables that we have declared within our state space up here. Okay. And so then what's this silly little program going to do? So we say basic prog. Well, it's got an input, hasn't it? It's a function from a natural. So for every possible natural, we can construct a program. And what this program is going to do, it's going to first of all assign 7 to x, the variable x. It's then going to assign big Y, which is the variable that we had as an input there to this function, to our state variable y. Now already you can see from this that we have 2 kinds of variables that we're going to need to deal with, and this is important. So far we've been dealing with logical variables. So you can remember when we wrote down lemmas and theorems and so on, we were permitted to have variables in there, right? And those variables were denoted by having a blue colour. So like here, right? So this is telling us this is a variable. Right, so those are logical variables, right? They're the variables of the logic which we're going to work with. But also now we have state variables, and these state variables are distinct. They're distinct from our logical variables. And so what we're doing here is we are basically taking it as input a logical variable and assigning this logical variable to a state variable. Now, if you've ever used Hoare logic, this is something that they do all the time, because in order to reason about programs, you need sometimes to be able to insert logical variables into them in order that you can capture things like invariance and so on. You don't need to worry about that too much at the moment. So you can just think, you can kind of think of this is a method. This is a, yes?
Sorry, I'm just confused. Which one is logical?
The logical variable is the green one, the big Y. So that's a kind of convention that you use in something like Hoare logic. So in Hoare, so when Tony writes down rules of Hoare logic, he typically will use a capital X and a capital Y to denote a logical variable, and the same lowercase letter to denote its program variable equivalent, right? So here we have to kind of write these French quotation marks around it as well, and that's just because of the parser, because it can't recognize the difference between. So if we just wrote y there, Isabelle would complain because it would try to parse y as a state variable, but there is no state variable called y, so it doesn't work. So that's why we have to put these quotations around it. And then finally, we're going to add together the 2 state variables, x and y, right? Now, you can kind of think of this as a method or something like that. So you can think of this y as a parameter of our method, and these as 2 kind of global variables, right, that we're making use of. So this is actually all explained in the text. So now that we've got this little program, what can we do with it? Well, the first thing that we can do is apply symbolic execution. So symbolic execution is basically allowing us to use the logical deduction facilities of Isabelle to execute a program. Right, so this is a symbolic program, right? This is a program which is denoted by a relation in Isabelle UTP. Exactly how it's denoted we'll come on to in a minute, but the point is this is logic. Ultimately, this is just logic internally. This is a logical relation. But what we can do now is we have lots and lots of laws that allow us to symbolically execute these programs. And so down here, what we're going to do is we're going to apply. So I'm actually abusing Isabelle a little bit here, and I'm hopeful that in the future, Jakub will show me the right way to do this. Jakub's an Isabelle expert, by the way, so I'm somehow a bit behind in terms of presenting things in a nice way, but He's my postdoc on CyPhyAssure, so he will undoubtedly make this better in the future. But in any case, so what we're doing is here, we're kind of setting up a fake lemma, right? So a fake theorem, and we're saying, okay, I want to try and execute this program, basic prog, with the input 7, and then this ID here is basically saying any initial state, right? So I want to execute this program with an arbitrary initial state. And so then we have this tactic SymEval, and you can, let me scroll that down, and you can see, once you run this tactic, it tells us terminated, x maps to 14, y maps to 7. So what this is telling me is if I execute the program basic prog with input 7, then when it terminates, x will have the value 14 and y will have the value 7. And that reflects our intuition, right, of what the program is doing. So it always assigns 7 to x, and then it always puts the input value into y, but then finally it also updates x so that it adds together the original value of x and the value of y that you've been given.
Why does the map still have _s?
Because it's S here stands for substitution. So I'll actually explain more about this in a minute actually, but essentially in Isabelle UTP, one of the things that we've done is unify together substitution and assignment. So this structure here is effectively is what's called a substitution. So it's stating that we're substituting 14 for x and 7 for y, right? And we can apply this kind of operator to a predicate as a substitution. You'll see more in the next thing, but you can just basically ignore those for the moment and just think of them as maplets. Effectively, they are just maplets. Another reason, why didn't we just use a maplet? Because Isabelle's already taken maplet and defined something else with it. So one of the things you'll find in Isabelle UTP is that sometimes we have to add subscripts onto operators because we've run out of syntactic symbols. But in this particular context, I've set up a nice parser. So you'll notice that at the top we imported UTP Easy Parser, which is supposed to somehow be easier to use, right? So that you can write down your programs in a more intuitive way than what the standard parser that Isabelle UTP gives you. So let's try this with a different input. So again, let's do. So as I say, this is a fake proof goal. So we're not actually trying to prove anything at all. We're kind of abusing the Isabelle simplifier. Yes. We'll talk about that offline, I think. I think that's above everybody's heads other than mine and yours, so we'll talk about that offline. Say if you can try it with some different inputs, make sure you can understand what's going on. Does everyone just put your hands up if you've got this working on your machine, this example? Good, excellent. So yeah, try and have a look at the person next to you. Try a few different inputs, see what happens. And feel free as well to change the program as well if you like. So we have other constructs in here as well. So for instance, I could change this to have an if then else inside of it. So something like if x is greater than 2, then we're going to do that. Otherwise, we're going to do x is x minus y phi, something like that. Right, so we can do if then else's. We can also do while loops as well, but we'll come on to while loops in a little bit. So one of the things I should have mentioned, by the way, as we're typing these things, I realise I should have said this right at the beginning. Isabelle supports these kinds of ASCII art representations of these symbols, if you hadn't realised that already. So, for instance, the funny double arrow that you can write, if I write an equals and an arrowhead, it will automatically turn it into one of those. The same applies for that kind of arrow. And there's a wide variety of symbols, actually, which Isabelle can make use of. So if you bring up the symbol tab down there, you'll see that there's a number of different symbols here which we can make use of. Lots of them, actually, lots and lots. And the symbol tab can be quite helpful if you don't know what you're looking for. Isabelle also supports a very similar markup notation to LaTeX. So for instance, if I type, what would be a good example? Langle, something like that, then it will auto-complete that. Now, somewhat confusingly, when the first time you use this, if Isabelle's autocomplete kicks in, naturally I think you want to press space or enter to get it to pick that symbol, but that isn't what you press. You actually have to press tab, and then it will autocomplete for you. The reason I was going to say that is because in order to write down this kind of goal, we need to write this model symbol, which you write as a pipe and an equals, and then it will autocomplete for you. So let's try a really big number, 107. Yeah. Mm-hmm.
Whereas you gave the rest of your lemon names.
Yeah.
So is that just if you use the quotations?
Yeah.
Or whatever you like then?
Yeah, so basically I'm just creating anonymous lemmas here, and this oops command, that basically means cancel this. So it means that I actually don't want to prove this now, so I'm going to cancel the proof attempt. And it's quite useful if you get halfway through a proof and then it's tea time and you need to go off and do something else. You just oops it and come back to it later, and it just makes sure your Isabelle theory still goes through. Yeah, so we're setting up an anonymous goal and then we're throwing it away because, as I say, we're sort of abusing the lemma syntax of Isabelle to do symbolic execution. All right, so another thing that we can do is apply Hoare logic. So Hoare logic, of course, is a very useful program verification construct. So we write things in terms of preconditions, postconditions, so Hoare triples. So we can write down these kinds of things. So we have to use, so if you've seen Hoare logic before, typically you write one of these in Hoare logic. Here we have to write two because that symbol is already taken for writing sets. Right, so here we have to write two of them so that we're not ambiguous. So what does this mean? So this is an assertion which says, if I start this program in a state where if I start this program in a state satisfying this predicate, then when it terminates, its final state satisfies this predicate, right? So if I start it in a state satisfying this predicate and I execute this program, then I'm going to get a state that satisfies that. So a very trivial example of this is the case where we don't care about the initial state, so we're just going to write true here. So true is just a vacuous predicate, it's always satisfied. So that basically means any initial state. And then in the final state, we're going to say that y has got the value y. And now you can see why we need this distinction, right, between program variables and logical variables. Because the scope of this logical variable is over the whole Hoare triple, right? So I can talk about this logical variable here, and I can also talk about it there. What I can't do is do the same with state variables, because of course the state variables here are referring to the state variables in the initial state, and here they're referring to the state variables in the final state. So if I want to be able to have a variable that goes over the whole Hoare triple, then I need a logical variable. So how do we prove this? So there's a tactic called Hoare auto. You run that and it says no subgoals. Now, what's actually going on in the background here? So Hoare logic, if you've ever seen it, has got a big deduction calculus associated with it, lots of different rules that you can apply to the different operators of your programs. It's got operators for sequential composition and assignment and so on, and we'll see some of those in the slides in a moment. But the crucial thing is it applies those rules for you, and then it comes up with a set of predicates that must be satisfied in order for this Hoare triple to hold. And these are called verification conditions, and this is a very, very common way of proving things about programs. Now, in this case, this is, of course, quite trivial to prove. And why is it trivial? Well, because if we looked at our program here, we always set y to be y. We always set little y to be big Y. We never do anything with it again afterwards, and so consequently, that Hoare triple holds trivially without having to do anything. Now, if I change my program up here, so let's say we also decide we're going to increment y is y plus 1, then that's not going to work now, and we end up with two residual proof goals, neither of which we can satisfy. In particular, we can't satisfy this one, right? So that isn't true. So if you get residual verification conditions that you can't prove, then you're messed up. Actually, there's another useful tool here. So I've showed you Sledgehammer already that allows you to do integration of automated theorem proving. We can also apply a counterexample generator called nitpick. Right? And what nitpick will try to do is it will try and find a counterexample for the formula that we're currently focused on. So for this particular case, it's given us a verification condition y must equal 0. So this we can only do this if y is 0. So can we find a counterexample for y is 0, a natural number? Well, of course we can. 1, right? 2. Lots of natural numbers are not equal to 0. So consequently, that's not going to work. So this means in Isabelle, you've kind of got this duality of tools, right? So on the one hand, we can do automated proof, but on the other hand, we can also attempt to falsify things. So we can say, well, is this falsifiable? And obviously, if it is, then you know that you can't possibly have a proof. So typically, when you're doing proof, one way to proceed is to, first of all, run your high-level automated proof tactics like induction and auto and so on, and then run Sledgehammer. If Sledgehammer times out, try nitpick. And if nitpick comes back with a counterexample, you know you made a mistake, and so then you need to go back. Right, and these are the kind of things that you can do. Let's go and correct our program so that it doesn't do that anymore. So get rid of that. All right. Okay, so that was a good example. Now, exercise 2. Does the following hold? And if not, why not? Actually, what I ought to do before you do that, if you've changed your program in the similar way that I did, unchange it, because that is going to make the exercise pretty silly. So this is the program we're focusing on. And so then the question is, does the following hold? You can ask Isabelle if you like. I don't mind. Sorry? Don't look at that. so this is because this is the internal syntax representation of Isabelle. So these U's are simply there to distinguish them from the built-in constants of Isabelle. So again, once me and Yaku work together a bit more, I'll try and get it so that not only, because at the moment there's a kind of disparity between what you're parsing and what you're printing, right? So the pretty printer down here is just showing the internal UTP representation, which is different and rather uglier. You've got all these ampersands and things hanging about. Both of those statements are true, because it is, so fundamentally it's defined in terms of Isabelle's less than. So I haven't redefined the concepts of what less than is. What I've done is I've lifted it into the expression model, and so that lifting is what that U denotes. But in practice, you should never have to type that. So you can just basically, if you see a U, just remove it in your head, just ignore it. when you see the output here. And the same for the ampersands, just ignore them in your head. Okay, so does this hold? Has anyone asked Isabelle? What kind of conditions? So let's try, see what happens. Well, it gives us false back, doesn't it? So So I put it to you that can never be true. It can never be the case that x is less than 1. And the reason for that is because x starts off at 7 and then we add something to it. And so that can't be the case. Now, if we change this, so we change it to x less than 10, now we get it's going to give us a condition back, right? So what I could do, if I wanted to make this go through, I could add an assumption here. And the way that I do that, the way that I do that is using this kind of, the way that I do that is by using a long double right arrow. So this is an implication symbol, confusingly. The short one is a function symbol. The long one is meta level implication. Sorry, Macarius. And that is probably the more logical way of doing it. Yes, Mario, you could well do that. So yes, so that's the alternative way. You just put in the logical variable y is less than 3, and then it would go through.
Methodologically, it is important to have this other option.
Yes. Yeah, because 1 is a kind of logical assumption. So you basically, the scope of the assumption is over the whole thing. Here, we're more making a constraint on the initial state. Right. But from a proof theoretic perspective, they actually end up being equivalent, more or less. All right, so we can correct that then. So that works. Okay, I think I'll leave the rest of the exercises up to you for another time. What I'll do now is come down to a more sophisticated example. Now we're going to connect with what we did previously. So in the first set of exercises, what did we do? We defined a functional specification for addition and for multiplication. What we're going to do now is write an imperative program for multiplication, right? So we do the same thing again. Again, think of this as a method, right? So this is a method, right, which takes two natural numbers as input and does a computation over the state space. And the idea is that this function is going to this method is going to multiply together two natural numbers, but it's going to do it as an imperative program now, which I guess most of us are much more familiar with how to do that. So what do we do? So we first of all assign the first input u to x. We then set y to 0. And then we say while x is greater than 0, I want you to ignore what comes after that for the moment. We'll come on to that in a minute. But while x is greater than 0, we're going to increment y by v, and we're going to decrement x. Now, hopefully you can see that this is effectively equivalent to what we were writing in the functional specification before, but in an imperative manner. So in each of our iterations, we are adding the value v to y, and we're decrementing x. You've got your two variables that you're multiplying. One of them you're increasing by this input v over and over again, and the other one you're decreasing. And then you stop once you reach 0. And so we can try this out. So let's use our symbolic evaluation engine again. And so if we apply SymEval with 8 and 8, we get the right value. We get 64. So you can see that we've now got, so what we've got here is basically the syntax of a basic imperative programming language where we have assignment, we have sequential composition, we have conditionals, we have iteration, and we can make use of all the different data types and functions and so on which have been defined in Isabelle already as functions within the context of these imperative programs. So that's quite nice. So try some other inputs. See what happens. We're trying to make sure that that our specification is correct.
Is there a reason why abbreviation may be marked in red and says that context for command?
It's because
Because you opened the ladder here, so that's just the wall. It's just telling you, okay, well, currently you could have got an open ladder if you were
Sorry, yes. Sorry, I should have
mentioned that. So if you've got a lemma which is open, so in other words you haven't got an oops or a done or something like that to close that, then you'll get an error. So for instance, if I get rid of this oops here, then the next lemma complains. It doesn't stop me, but it complains. It says bad context for lemma, and that's because we're still in the context of this lemma. So our proof state isn't quite right, and we can fix that by going oops. Does our multiplication program seem to work correctly? You sure? I'm sure it works correctly. Yeah. Yeah. So that, I'll show that actually, because so this is symbolic evaluation, right? So this is not at all efficient. So yeah, if I put, well, let's be brave. By the way, if you put a non-terminating program in here, this is what you would see, and this wouldn't stop. So it would just continue. So this purple, which is now gone, the purple means Isabelle is thinking, basically. It's trying to execute this. So that's great, so we got the right value back. But yeah, it takes a long time, right? Because, of course, you don't really want to be using this to execute your programs. This is more for testing them out. So yeah, that's right. So if we made a mistake in this algorithm, so let's say I made this little mistake. Now, can anyone see the problem if I do that? So I've just changed the loop condition. What's the issue with that? You won't just do an extra iteration. So actually this is quite subtle. And this is because, so can you remember what the type of x and y is? X and y is a natural number. So when you reach 0, and 0 minus something for a natural number is undefined, although Isabelle actually says, no, it's 0, actually. And so what that means is that this will not terminate. So if you try it, it just goes on and on. Never ending. And this is partial correctness, right? So we're in a setting where we can have programs that don't terminate. And if they don't terminate, not much we can say about them, really. Which coincidentally is one of the reasons that you sometimes want to go beyond this simple relational model so that you can encode extra information about termination. But let's turn that back. Yes. No, because minus is, so Isabelle is based on total functions. So there is no concept of undefinedness as a core concept in Isabelle. You can get undefinedness, but you need to explicitly encode it. So what the consequence of that is that every function in Isabelle is a total function. Consequently, minus is a total function. So 0 minus 1, according to Isabelle, is 0. 0 minus anything, according to Isabelle, is 0 when you're a natural number. So what that means is that it won't detect that. It will be 0 and it will stay as 0. And I mean, another way of thinking about it is actually, so if I write down a lemma, x of type natural greater than or equal to 0, because of a capital X, then it will tell me that this is actually, so I can prove this, and that means it's a tautology. And if it's a tautology, then that means that effectively what I've got here is while true, right, if x is greater than or equal to y. And of
So the minus function is not defined as natural to real, but natural to natural.
Natural to natural. So if you want, if you want to be able to reason about it that way, you need to be able to explicitly talk about. So you have integers as well. You have rationals. You have reals. Natural numbers just don't have the capability of reasoning about negativity. So yeah.
So could I justify my own subtraction on the naturals?
Yeah.
Introduce an extra symbol.
Yeah, you can do that. Yeah.
That detects this
Yeah.
error.
And that's exactly what I mean by encoding partiality, right? So you're basically adjoining your set of naturals with an additional element that would denote undefinedness. And we have a theory of undefined expressions in Isabelle Hall, so that you can have expressions that are potentially abort, basically. And so, but we're not. But in this basic, so we're already seeing deficiencies, right, of this relational model. There are things we can't quite reason about as yet. So we can see that, right? So the relational model is very powerful, but there are things that are missing from it. And this is why we need UTP theories, of course. I mean, of course, on a more basic level, we're quite limited in terms of the operators that we've got here. We've got no pointers, right? We're just talking about assignment and if then else and while loops and so on. We've got no parallelism, we've got no threads. There's lots of things that are missing, right, from this language. So that's why we need to be able to enrich it with additional information. But nevertheless, let's continue with this basic relational language for now. So now what we're going to do is we're going to link together with the functional, the functional part of Isabelle a little bit more. So this Hoare triple, what this tells us is that the multiplication program, so if I do multiply u and v, and I start in any state, then in the final state, we're going to have y being equal to u multiplied by v, but this is now the function multiplication, right? So here we have our function multiplication that we defined earlier, or could have defined earlier, right? And then we reasoned about it. And then we have our imperative program multiplication. So effectively what we are showing here, using Hoare logic, is that our imperative program multiply implements the functional specification given by this one, right? So this is like a refinement that we're doing here. We're refining a functional specification into a deterministic imperative program that we can execute. So if we use our Hoare auto tactic here, we get something back, right? We've got a verification condition, right? So it's not trivial. So we're going to need some properties of our functional multiplication in order for us to do this. So you'll note down here, all of our state variables have disappeared, right? So this is a logical variable. You don't need to worry about it being green. It's just because it's explicitly quantified. But this is a logical variable that corresponds to our imperative variable that we had at the top, right? But this now is purely a whole expression, right? So there's no UTP here at all. This is just a whole expression. And so now what I can do, I can apply sledgehammer to this. It says proof found. Hurrah. It's found the property that we needed. And we can go and look at that property if we want to. So you can control click on that, and it will take us into the theory of natural numbers and showed us the property that we needed to do that. And actually this property is just showing a relationship between suc and minus when n is less than or equal to m. So I think this actually illustrates the case that you were talking about, Mario, right? Because that's why you need this guard, because otherwise, if you have if you're trying to take away an n which is greater than m, then these kinds of formulas don't hold. Okay. And by the way, to go back, there's an arrow up here, back, and then that takes us back to where we are. So now we've got a system where we can do automated verification, right? So Hoare Auto is a tactic that allows us to get verification conditions for a simple imperative program, and then we can combine that with Sledgehammer in order to discharge our verification conditions. So essentially what we want to do with UTP is now to push things in these two different directions, right? So we've seen some deficiencies in the relational model that mean that we can't model everything that we'd like to. So we're going to add additional computational paradigms that allow us to deal with that issue. And on the other hand, we're going to develop different semantic models. So what I'm going to do now is I'm going to drop back to our slides, and I want to tell you a little bit more about the foundations of how this actually works internally. So before I do that, does anyone have any questions about this? Did people manage to get this example to work? You're able to follow on your laptops? Good. Good. Feel free to try and verify your favorite algorithm. Okay, so back to the slides. So as I said, hopefully you can see from this that we have really been making use of two different semantic models. So to do symbolic evaluation or program execution, we need operational semantics because we need a way of stepping forward a program. But to do Hoare logic reasoning, we need an axiomatic semantics. Now, what UTP allows us to do in one axis is to unify together all of these different semantic presentations. And the way it does that is by using denotational semantics. So all of the programming operators that we've been using so far can actually be written down as predicates. Again, this is the programs as predicates approach that was created by Eric Hainer. Now, in mathematical UTP, a conditional is written like this, right? So this sort of infix notation for conditional. So B here is the condition, P is the if branch, and Q is the else branch. And the reason for doing that will become clearer in a minute. Basically, it means that writing down algebraic laws for this is much easier. It's just much more intuitive to work with this for algebraic laws. So we can give this a denotation as a predicate. So B here is a condition, so it doesn't refer to any output variables, sorry. And P and Q are both relations. And the way that we denote that is B and P, or not B and Q in logic. So what that means is if the condition B is true, then we're going to enable all of P's behaviors. If B is not true, we're going to enable all of Q's behaviors. And that's how we can denote that kind of operator. Sequential composition requires a little bit more thinking about. So we write this in a slightly different way just to help with understanding. So we're going to say that we've got some vector of variables that our program is working over, which we're going to call V. So this is the sum of all the variables that we have in our program. So P is going to depend on the after values, and sorry, we're explicitly referring to the after values of P, which is why we've got this V primed here, and to the before values of Q, which is why we've got this unprimed V here. And then what we're going to say is that there exists a V0 such that P holds a V0 and Q holds a V0. And what this V0 is the intermediate state between executing P and Q. So effectively what we're doing is we are connecting the outputs of P to the inputs of Q. And if you've seen relational calculus, this is the kind of definition that they use for sequential composition. So in order for us to be able to compose two programs together, we're really saying that there exists a set of compatible intermediate states between them, right, which is what this existential quantification means. Okay, assignment for a set of variables x, y, z. So we explicitly write the set of variables on the assignment here. In Isabelle UTP, this is done for us automatically. Because alphabets are types, we can use type inference to work out all the variables we've got and then to give the semantics for this. But essentially what this is saying is that an assignment of some expression to some variable x is equivalent to this predicate here that says x prime takes on the value e, y primed equals y, and all other variables remain the same. And that's how you denote an assignment. Yes, Marie? Mm-hmm.
Then when you do refinement and you want to change the value of y,
Yeah.
you get an error.
Yes, so you can't. So if you write down an assignment, you can't refine an assignment into something other than something that leaves the variables the same. So if you want to be able to do that kind of refinement, you can set up a more explicit frame operator, and we have these kinds of frame operators in Isabelle UTP as well. I'm afraid I'm not going to go there today, but yeah, we can. So what you can effectively do is you can say, well, okay, I'm only going to think about this subset of variables, and the rest of them, their behavior can be arbitrary. So yeah, you can do that kind of thing. But for the assignment operator, you wouldn't use that for that kind of specification.
And that's the implementation that's a way of implementation.
Yes.
I only ask because in event B, in some of the literature, it says it's not allowed to change.
Yeah.
When you use the tool support, actually, it's allowed to change.
Yeah. And so you can make your own choice in Isabelle UTP basically. So we support a wide variety of different framing conditions. So you can say all of these variables stay the same, or all of these variables are arbitrary. It doesn't matter. So yeah, it's interesting you mention event B, because I'd quite like to be able to add a kind of event B like front end onto this in future. But yeah, that's something to think about. Okay, so that's an assignment. We then have a special assignment, which is written like this, which is just a skip, so leave all variables the same. And then we have an iteration operator. Again, this is using our fixed point operators, so I'll just try and give you the intuition of what's going on here. So it's written in terms of a conditional, so what it says is that if B is true, then we're going to execute P, and then we're going to recurse. Otherwise, we're going to skip, right? We're not going to do anything, which is the behavior of a while loop, right? And that's it. So that's the denotational semantics of our imperative programming language using the programs as predicates approach. Okay, so what can we do with this? Well, the first thing we can do is we can create an algebraic semantics, right? So these laws... Oh, I've lost my battery. Excuse me. So these laws are all theorems of the definitions that we saw on the previous slide, right? So these are all things that can be proved, and actually all of these laws have been proved within Isabelle UTP, right? So if you want me to show you, I won't do it now, but if you look within Isabelle UTP in the documentation, it will show you. It will show you about all the proofs of the laws that we can do. So all of these laws are very easy to prove, and we have a proof tactic that allows us to prove them. So let me just go through them very briefly, one or two maybe. So idempotence of conditional. So if I have a conditional where you've got B in the middle and P on either side, well, that's just P, right? Because I'm not actually presenting a choice. The behavior is just the same. I've got this kind of symmetry law for if then else. So what this says is that if I have a conditional, then I can commute it, right? And this is why UTP writes if then else in this kind of infix fashion, because it sort of suggests the more algebraic nature of the operator. And then we have other stuff as well. So for instance, if I have a true condition, then of course that's just P. If I have a false condition, precisely the same. We have these kinds of, so this is called the conditional concealment, so or the shadowing law. So what this says is that if I have a conditional on the outside on B and then another conditional in the then branch on the same B, then I can basically just drop out Q because it's an unreachable branch. You can never get to Q. And so this kind of law is useful for doing program analysis, right? Because if you have such a program where you have this unreachable branch, then probably you've made some kind of mistake. Or you've got code there that can never be reached. So yeah, so this is why these kind of algebraic laws are useful. And we have a whole load more, which I'm not going to go through. Sequential composition is associative, which I guess is not overly surprising, and I guess we'd want that. And conditional can distribute through, sequential composition can distribute through conditional from the right to the left. Now, is it the case going in the other direction? Can anyone hazard a guess? So let me just explain a little bit more about what this is doing. So if I say, if B then P, else Q, followed by R, well, I can just push this R into here on both sides, right? Because you're going to execute R, whatever happens, so you can push it into both the if and the else branch. Is it true the other way, Jakub?
So you can't, and there's two conditions. Either the left relation should not be empty, otherwise it diverge.
Yeah.
Or say something completely out of it.
Yeah. So basically the answer is no. And the reason that the answer is would usually be no is because if I have a conditional here on this side, then what came before the conditional may well have changed the variables in B, right? So you can't distribute the other way. So these kinds of algebraic laws are kind of helping us to understand more about the intuition for these operators. We have similar laws for assignment. I'll again just pick one or two. So if I have an assignment before a conditional that talks about X, then I can push that assignment through the conditional, provided I substitute X for the value that I assign to X. So you see this assignment ends up on both sides of the if then else branch. And we can say that skip is a left and a right unit. So these are called the laws of programming. So Tony Hoare and some others, Bill Roscoe and so on, they wrote a paper in 1987, I think, called The Laws of Programming, that was basically trying to give a comprehensive set of algebraic laws for imperative programs. And these are some of those laws. Non-determinism is not interesting. I'm going to skip over that, but this is a proof, basically, of showing how we can compose two assignments together using these laws, but we don't really have time to look at that in detail. All of these laws can be proved by Isabelle. Yes, so we'll skip that one as well. All right, so that's algebraic semantics. Now, how do we do axiomatic semantics from this base? So a Hoare triple, well, we know what it means. How do we denote it? The answer is like this, or more helpfully, perhaps like this. So we can rewrite a Hoare triple as an assignment. So what's happening here is that we are constructing a specification that says my precondition implies my postcondition. I have to put this prime here because R is talking about unprimed variables, and so I just need to modify it so that R is now talking about after variables. So in other words, if P held on the initial values for my variables, then R will hold on the final value of my variables. So that's our specification. And then what we do is we say, and Q refines that specification, right? And it's interesting because a lot of the time in UTP, you end up being able to write things ultimately down as refinements. Right? So Hoare trickle just ends up as some kind of refinement. And the same goes for a number of other axiomatic semantics. Now, why is this useful? Well, because now what we can do is we can prove all of the laws of Hoare logic as theorems of this definition. I won't go through all of the Hoare logic laws. You can look these up. These are pretty standard. I'll maybe just pick one out. Yeah, let's pick the one for conditional. So how do I show that? So if I have a conditional like this with precondition P and postcondition R, how do I show that this satisfies this pre-post condition pair? Well, I have to consider the if branch, and of course in the if branch I can assume that B is true because you're in the if branch, and on the other hand, in the else branch you can assume that B is false. Right? So you have to show that both branches eventually reach the post condition, but you can conjoin them both with the condition both in its positive and negative form. And you have similar laws for other ones. Now, the point you see here is, so how does Isabelle UTP work? Well, we prove all of these laws, you say, inside of it, and then we load them into this proof tactic Hoare Auto, and Hoare Auto automatically applies all of these laws and allows us to reason about our program. We can also do weakest precondition, but I don't really want to go there. If you're familiar with weakest precondition calculus, it's another axiomatic semantics for programs created by Dijkstra, I think, originally. It allows you to write down assertions like this that basically says, find me the weakest precondition of P such that the postcondition Q is satisfied. And that's what that formula means. So it's a kind of calculational approach to determining preconditions called the weakest precondition. And there's a link between WP and Hoare, which I don't have in these slides, unfortunately. But another thing that you can do in UTP is link together different semantic presentations. And the reason that you can do that is because ultimately everything is just denotational semantics, right? So everything that we have presented following the denotational semantics section are all theorems, right? They're not laws that we're just writing down. They are theorems of the definitions. And this is the whole idea of denotational semantics, right? Everything ultimately just becomes theorems of your definitions. So let's conclude, and we'll take a break in a moment. Operational semantics. Now, operational semantics, in some sense, is the hardest of these to think about, but let's see if we can understand what's going on. So operational semantics, again, is what underlies our symbolic evaluation engine in Isabelle UTP. So the first thing I'm going to need to do is I'm going to need to answer Mari's question in more detail, which is to explain to you how we have generalized assignments. So who here has done who here has created an operational semantics in the past or read one? Right, so you'll be familiar with operational semantics. A very important thing to be able to represent is an evaluation context. So you need a way of being able to write down what are the present values for all of my variables, right? That's something that you want to be able to do. Now, it turns out that, so there's a computer scientist called Ralph Johann Bach who wrote a book called Refinement Calculus. Excellent book, by the way, if you get the opportunity to read it. In Bach's refinement calculus, he has a generalized assignment operator. Right, so typically assignments are written down in the way that we have, right, where you write a variable and an expression. In Bach's work, he doesn't write an assignment like that. He writes it as a function, and specifically a function on the state space. And that's what this operator is here. So this small-looking operator here is actually very important to how operational semantics in Isabelle UTP work. So if we think of an alphabet A, then we can think of sigma as a function from A to A. So this is a function on our state space. It's telling us how we can update our state space function-wise. And that turns out to be very, very, very helpful and very general, and a nice algebraic way of reasoning about assignment. So how do we denote this? So if sigma is a function on our state, then all that we have to do is say v prime, so the entirety of the state afterwards, so all of our variables, is going to be equal to sigma applied to our initial state. So this is just like a function application. So sigma can be thought of as a state update, right? So it maps the original state to a new state, and we can construct them using these maplets, right? So these are telling us valuations for each of our variables as expressions. We can also apply these state updates as substitutions to expressions, and so we have this funny dagger notation, which basically this kind of gives the intuition below for what these two operators are really talking about. So we can now generalize our singleton assignment operator, so assign v to x, to be the generalized assignment with the substitution that maps x to v, right? And that's all it is. It's not particularly magical. And similarly, for this sort of classical substitution, where you're substituting one variable for some expression v, this can be written down as this kind of substitution. So again, we construct a substitution that maps x to v and we apply it to e, right? And this is really nice because now what we can do using Back's result, we can unify assignment and substitution together. And in particular, we can use substitutions to construct operational semantics. We can use these things to denote our evaluation context in an operational semantics. By the way, a nice thing about this generalized assignment operator is it follows some nice homomorphic laws. So if I have the identity function inside, then this is just my skip function, so all variables remain the same. And if I have sequential composition of two assignments, I've made a mistake here. So this is function composition, so this is the other way around. So this should actually be row this should be row after sigma. So that's actually the wrong way around. But hopefully you can see the idea that we can now use function composition to connect together state updates. So then how do we do operational semantics? Well, it actually turns out now to be quite easy. Because if I want, typically in operational semantics, you want to be able to write down these kinds of things. So the evaluation of program P under context gamma, we can simply denote this as sequential composition. So we take our evaluation context, we turn it into an assignment, we pre-compose it with our program P. So this denotes all final states of P when started in a state gamma. And now what we can do is, we take all of our algebraic laws that we proved previously, and we can turn those into operational semantic laws, which then allows us to do symbolic evaluation. So here's a simple example. So if I've got a very simple program that just adds 1 to x, and I start it in this context where x has the value 2, then I can now apply my algebraic laws to symbolically evaluate this. So the first thing that I do is I unwrap this, so this is now just a sequential composition. I then apply generalized assignment and substitution, so I've replaced my value x here with this value there, and then of course I just use arithmetic. And so if I start the program in the state where x is 2, and of course in the final state x has the value 3. From this, we can then prove as theorems all these operational semantics laws, right? So let me just talk these through, and then we'll have a break. So the way to read this is that this operator here, so gamma entails skip, denotes a program that has terminated in state gamma. So do you remember when we applied the symbolic evaluation tactic and we got these things terminated, blah? That's exactly what this means. We terminated in a state, in the state gamma. This operational semantic arrow is actually just equality, right? But we're going to orient it in a particular direction so that we can then apply it from left to right to execute our programs. And then we have all of these kinds of laws. So let me just pick one out. So if I have a terminated execution followed by P, then I can start executing P from the final state of the first program. I can apply assignments simply by composing them with existing context. If I have an if-then-else, and so if I apply gamma as a substitution to my condition B and I get true, then this will just, so Q will drop away and you'll just be evaluating P, and likewise for the other branch. And you have similar cases for while programs. So now we have all of these theorems that we can do operational semantics with. And the final thing I'm going to say before we break is we can also prove a useful linking theorem. And what this linking theorem does is it connects together Hoare logic and operational semantics in, I think, an intuitive way. So if we start P in a state satisfying B, then we know that the post condition then follows C, then what does this mean? It means that for any two evaluation contexts, gamma 1 and gamma 2, if B satisfies gamma 1 and we executed P from state gamma 1, then in the final state, C will satisfy gamma 2. And that's the intuitive operational meaning of a Hoare triple, right? If I start a program in a state that satisfies B, then I'm guaranteed, then when I execute it, I'm guaranteed to end up in a state that satisfies C. Okay, I think we should take a break at that. So I've been making this argument, right, that Isabelle UTP is sort of a platform for doing integrated formal methods. Now, at the moment, all that we've looked at so far is these simple imperative programs. So what I want to do now is kind of come a little bit more, excuse me. I want to come a little bit more sort of top down and think about how this works out practically. So we've seen these kind of verification technology that we can create, right, where you have a high-level tactic like Hoare Auto that allows you to create verification conditions and then use of sledgehammer for discharging those verification conditions. Now that approach is not only applicable to imperative programs, but this is essentially the fundamental approach that Isabelle UTP takes to verification. So if we think of a language like RoboChart, so let's go much more high level now, right? So we're not just thinking about imperative programs anymore, we're thinking about state machines, right? So these kind of state machine diagrams that you can have. So you have states, you have transitions between them, you have variables within them, and you have channels that these state machines can communicate with. So we're talking about concurrent reactive systems, essentially. So this, I guess we were all here for Anna's lecture, but this RoboChart language, so this was developed basically for describing robotic controllers. And one of the things that we've done is we've used Isabelle UTP to give a denotational semantics to this language. And the way that that works is, first of all, we have to enrich our theory to a theory of reactive programs. So who here has heard of CSP, communicating sequential processors? Very good. So one of the achievements of Tony Hoare's original book was to show how to give a predicative semantics to CSP, right? So the traditional semantics for CSP is called the failures divergences model. And the way that that works is you're basically giving a trace-based semantics to CSP, so sets of traces, more or less, plus refusals and some other information there. What they did in the UTP book is they turned this into a predicative semantics. So you still have traces, you have refusals, but it's presented in a predicative style. I'm not going to be able to go into that in detail, unfortunately, just because of time and for me not wanting to bore you too much. But the crucial detail here is that, so we can use UTP to describe reactive programs which have both internal state associated with them, like we already saw with the imperative programs, but also can communicate on channels. And I'd like to show you an example of how this works. So here is a RoboChart example. Now in Isabelle UTP, we have developed a command, a top-level command that allows you to write one of these state machines down. So obviously this is in a browser window. I'm sorry, I don't have this this on my laptop at the moment, this particular example. But this is an Isabelle command that we've created. And what this Isabelle command allows you to do is, so you declare the variables that you have in your state. So you can see these are all kind of the sort of variables that we would declare before, right? So these are all Isabelle types that we've declared. We have a number of events as well. So in this case, we have an event resume, stop, turn, and some other stuff. We have some states, which were in the state machine diagram we saw earlier. We have an initial state, init state, and we have some final states. And then we have a collection of transitions, right, which show how you transition from one state to another. And essentially, this corresponds precisely to this state machine up here, right? So we have our events, and we have a number of different transitions. So for instance, here, if we're in the reading state, then so this is a kind of CSP style input. So we're saying input on the gas channel, the value GS. And then we have another state here, analysis, which is going to update another variable, STS, to be analysis of GS when you as an entry action. So this is quite similar to UML, SysML state machines. And so yeah, so this command will generate a denotational semantics for this state machine in terms of a reactive program. And we've developed proof tactics that are similar to the ones that we've seen already that allow us to prove properties about this state machine, prove invariance about this state machine. So for instance, one of the invariants that you typically want to show is that your state machine doesn't deadlock. So in other words, you can't end up in a state where no transitions are enabled. And that's the kind of thing that we can use Isabelle UTP to prove. So this is one example of some of the things that we've done with Isabelle UTP. Another example, aside from state machines, we can also think about hybrid systems. So hybrid systems, you have differential equations, and you have continuous variables. And so one of the other theories that we have developed in Isabelle UTP allows us to put ordinary differential equations, to write down relations with ordinary differential equations inside of them. And one of the things that we're working on at the moment is integrating, based on Jonathan's work that he spoke about earlier, differential dynamic logic into Isabelle UTP, so that we can use Isabelle UTP to reason about hybrid programs, so programs which contain differential equations and can describe continuous dynamics and so on. So that's just to try and sort of illustrate a little bit more of the breadth of sort of the things that you can do with the tool. Now, in terms of how this works, I just want to tell us a little bit about how we build these building blocks. So hybrid computation, real time and so on, as I said, these can be characterized by these things called UTP theories. And it's essentially a UTP theory. So the programs that we've seen so far, we have a collection of variables associated with them, and those variables denote program variables. So they're the variables that we can assign to, that we can manipulate in various ways. However, there may be a different class of variable that we want to have, as I hinted at the beginning, which are what we might call observational variables. Right? So these are special variables that allow us to encode kind of properties of the program or properties of the real world. So for instance, we might have a variable called clock. Now clock, if we have such a variable, which represents time passing, that's a peculiar kind of variable in as much as we can't assign to it, can we? Or we shouldn't be allowed to assign to it because I can't just specify what time I want it to be at the moment. So no, there are constraints on how this kind of variable can behave. And this introduces the idea of healthiness conditions. So essentially, a UTP theory is a constrained semantic domain consisting of observational variables and invariants over the observational variables that explain how those variables are permitted to behave. So let me give you a simple illustration of this. So far we've been dealing with these basic imperative programs. Let's add time to these programs. So what we're going to do is, so as I said, a UTP theory consists of three parts. So first of all, we have our state variables. So we're going to have an alphabet, which consists of the different observations that we can make. And in this case, we're going to have two of these. We'll have a variable called time, which is going to represent the passage of time. And we're going to have a variable called st, which is going to be the state of the program. And then the predicates within this theory are the relations over these variables. And our relations need to be reasonable then, right? So we don't want to be able to reverse time. And so for that reason, we introduce what's called a healthiness condition. So this is the constraint that we want all of our time programs to obey, that time is less than or equal to time primed. Yes?
But will it hold in the real world? So, for example, if you have a multiple processor,
Yeah.
and you use a usual Linux system with a usual Linux scheduler, your program can be switched to a different core.
Mm-hmm.
And when your program gets real-time clock on a different core, you can actually get earlier time,
Mm-hmm.
a later point in time
Mm-hmm.
on a different core. So that
Mhm.
can hold
Yeah.
in real computational line,
Yeah.
but also synchronization of clocks between
Yeah.
systems.
Yeah. So the model of time can somehow be imperfect, certainly. So here we're kind of representing a sort of idealized. So this is a very simple theory. So sure, you can have theories where time can kind of skew and do strange things. Here we're just assuming very basic real-time programs where time is always advancing. Sure. So and that kind of motivates why you want more advanced UTP theories that allow you to write different kinds of invariants, right? But this is just kind of a motivating example, right? So this isn't actually how I say that we should model real-time programs, because it's very basic, but it's to sort of illustrate how it works, how the idea of a UTP theory works. So then the way that we encode our healthiness condition, so this is the dynamic invariant that we want our relations to obey. Time is less than or equal to time primed. And the way that we encode that in UTP is by means of a function on predicates called a healthiness condition. So this function ht, if I apply it to one of my programs, it will ensure that time is less than or equal to time primed, right, for all observations. Right, so let's drop into Isabelle, and we can see how this. Right. So here, what we're doing is, so we're doing exactly what we said. So we're creating an alphabet for our theory, right? And this has got our two variables associated with it: time of type nat and st of type s. Now, so this is parametric now. This is a parametric alphabet, so we can actually add any other state space that we like as a parameter to this. So I can add whatever program variables I like, and then it will just carry it as a parameter. We then create a type of timed relations, and these are simply going to be relations, homogeneous relations over this state space. ST type. State space isn't quite the right word, because we're not really talking about the state of a program now. These days I prefer to talk about observation spaces, because you're really talking about the possible observations that you can make. And this is the essence of the UTP approach, right? And indeed the essence of abstraction, right? That we're thinking about, what do I want to observe of the real world? What am I going to omit? And how do those quantities of the real world behave, right? And this is really what your observational variables are encoding. So we encode our healthiness condition here. So it has this function. Again, apologise for the slightly nasty syntax, but the dollars, they just denote relational variables. So this is time and this is time primed. So this then is the healthiness condition. So the way to think about this is that the set of well-behaved timed programs is the set of fixed points of this function. So what do I mean by that? I mean that they are the programs which precisely obey this invariant. We'll see an example of that in a minute. But here's an example of one such well-behaved time program. So this is a wait operator. So here what I'm doing is, right, so we've got all of these other programming operators defined already, and we were using them in the last session. So we've got sequential composition, we've got assignment, we've got loads and loads of things. Now what we're doing is we're enriching our language of relations with an additional operator to represent a delay. So this delay operator takes a natural number and produces a timed relation. And what it says is that time primed equals time plus n, and the state remains the same. Right, so the state is unchanged by a delay. So we introduce this delay into our program. Now, typically for healthiness conditions, you want to prove two proof obligations. So the first is our healthiness condition should be idempotent. And what does that mean? It means that if I apply the healthiness condition twice, it's going to have the same effect as applying it once. I can't make my program more healthy if it's already healthy. So that's a property that we want to prove. We have an automated proof tactic in Isabelle UTP called rel auto, and rel auto allows us to discharge a wide variety of relational goals. So by the way, so the imperative programs that we were dealing with previously, they're essentially syntactic sugar for these kind of relational specifications, right? So we're dealing with exactly the same kinds of things that we had previously, but now we're writing our primed and unprimed variables explicitly, right? But of course, once you start to use these in a program, then you just work with these operators, right? And this is the essence of denotational semantics. You denote your operators and then you use them. And once you've proved your laws about the operators, you don't actually need to care about the denotations anymore. All that you're interested in is the different semantic models. So here what we do is, so we prove that it's idempotent by rel auto. Another useful property is that it's monotonic. So that means it preserves refinement. So if I can show that P is refined by Q, then I can also show that HT of P is refined by HT of Q. And this follows simply because conjunction is monotonic. So let me show you that. All right. So that's fine. Now, as a side comment, since we know that our healthiness condition is monotonic, that means that we can invoke a theorem called the Nasta-Tarski theorem, which tells us that our set of healthy programs forms a complete lattice. So there is a bottom, there is a top, there is a meet, there is a join, and there are least and greatest fixed point operators. So that now means I can talk about, just by knowing this, I can automatically justify talking about recursive timed relations. But we're not really going to go there. But these are the kinds of properties that you can make use of when you're writing your theories. So here's a couple of examples. Is this a healthy timed relation? Is time advancing? Is time less than or equal to time primed? I agree. Yeah, so it can do that. So this is an example of a healthy element of our theory, right? How about this? Why not? Time, yeah, we're endeavouring to reverse time, right? And if we try to do rel auto on that, we'll get a similar situation to we did before, where we'll end up with a proof obligation left over, which is telling us that time is less than or equal to time minus 1. And then what I can do is I can invoke my counterexample generator, nitpick, on that, and it will, of course, find me a value of time for which this doesn't hold, and so clearly it was wrong. On the other hand, my wait operator, if I apply HT to that, that is healthy, right? And because the wait operator always advances time. What I typically then want to do, so another way of writing that, another way of writing this kind of goal, and the typical way of doing this in the UTP is to say that some operator is something healthy, right? So this simply means that wait is a healthy operator of our theory. So typically you'll see these kinds of things. So wait is HT, just means that wait is a fixed point of HT, which of course it is. But some of our other operators will be healthy elements of our theory as well. And what this is going to now allow us to do is to start sharing some of the operators that we've defined previously within this domain. So for instance, the relational skip operator that we defined, that is healthy, right? And the reason it's healthy is because relational skip simply leaves all variables unchanged, and consequently time doesn't change, and so it is less than or equal to, time is less than or equal to time primed. On the other hand, the sequential composition of two timed relations is healthy, and this of course follows by transitivity of less than or equal to. So if I apply rel auto to this, you're going to get some big predicate, but essentially this is not difficult to deal with, so we can then sledgehammer that. And yeah, it gives us order transitivity. So the order on natural numbers is transitive, and so the sequential composition of two timed relations is healthy for that reason. Okay, so that's kind of proved the basis of our theory. Now what we can do is we can start to prove some algebraic laws. I'm afraid I haven't done very many of these. This is just sort of to try and give you the idea of how UTP theories work. We've got our denotational semantics. Now we can start to construct our algebraic semantics. So what's this telling us? It's telling us if I wait 0 time units, then this is just the same as a skip, right? Because if I wait no time, then nothing happens. And that goes fine. All right. And then, finally, this operator. So what this is telling me is that if I wait m units and then wait n units, then this is just the same as a single wait on m plus n. And of course, this too is a theorem. Now, what we could do now is if we're able to completely define our algebraic semantics in this way, we could then also, in the same way that we did for relational programs, start to create a Hoare logic for these simple timed programs, a symbolic execution engine, and all of these other things, right? And obviously, this is a really simple theory, right? I mean, it's not particularly exciting, but this is the essence of the UTP approach, right? So we characterize these theories, and then we use these theories to develop these analysis techniques based on them. And so what I'd like to do, just to finish off this tutorial, is to show you a more substantial example, which is of a reactive buffer. Now, so the first thing that we do, sorry, I'm calling it buff with two Fs here, but never mind. So we have our two state variables, buff and val. So we didn't have a val variable here, actually, so I've done it slightly differently here, but you'll see how it works. But we do have our input and our output channel, and this is represented using an algebraic data type, right, that we've worked with already. So now we're kind of putting together all the different ideas that we've thought about. So we have an alphabet that contains our state variables. We have an algebraic data type that contains our channels. We then create some useful type synonyms. And I'm actually going to split this up a little bit from what we had there. So this is our initial action. So this is what happens right at the beginning. So we're just going to set buff to be empty. It's worth noting this assignment operator, yes,
When you define channels at the top of the data type two,
yes,
am I right in saying this is completely separate from FDR?
yes, yes. This is not FDR. So this is,
But it doesn't output to an
it doesn't, sorry,
you can't take the CSP part out to use FDR.
no, but that would be a cool thing to do, wouldn't it? One thing we have thought about doing in the past is trying to somehow support CSPM as an input format into Isabelle UTP, but we haven't done it yet. And CSPM is quite a complex language, but in theory you can do things like that because you've got all the power of functional programming language here. Plus now we've got CSP processors, well, Circus processors technically. Okay, so now we've defined the main behavior, and hopefully you can see that that corresponds to what we had there. So the two options are we input over our input channel and place the value in the val variable, and then we extend buffer by that. And then we've got the second option, if the size of the buffer is greater than 0, then we can take the first element of that buffer, send it out over the output channel, and then remove the first element of the buffer. And then the entire buffer is just this infinite loop here, right? Now, how do we verify this? Well, again, in a very similar way to what we've shown so far. Internally, what we're doing is we're creating an axiomatic semantics for reactive programs, and I have a notion of reactive contract, which I can't go into in detail, but very briefly, in Hoare logic, you're dealing with pre- and post-condition. In reactive programs, you have to have an additional part, which is what we call a pericondition. So you have a precondition, a postcondition, and a pericondition. And the reason you need that extra part is because Circus processors can both be in quiescent observations, which means they're awaiting some input from the environment, but they can also terminate as well. So we have both terminating and quiescent behavior because we're reactive. Right? So that's why we need that. But I can't go into reactive contracts now. But essentially, you end up with something that looks like a Hoare logic, but has got this extra bit in the middle.
Can I ask a very specific question?
Yes.
So, in the while loop, the condition simply not so orthogonal, so the input channel can have an input value,
Yes.
and the buffer can be still
Yes.
non-empty.
Because so this is non-deterministic. This is a concurrent program, so it's non-deterministic. So we're presenting options that the environment can do. So sure, so we can put lots of stuff in, and we can interleave that with taking stuff out as well.
Right. And then the second question is that I don't see where bounding comes in. The buffer that
Sorry, I said bounded buffer, didn't I? I apologise for that. I didn't mean to say bounded buffer. So you can bound it by adding another variable, and then, I'm sorry, I don't know why I said bounded buffer. I think I've got that in my head for some reason. No, this is an unbounded buffer, absolutely. Cool. Okay, so then let me, I can't go through exactly what's going on here. So this is one of these reactive contracts, and what we're doing here is well, I'll not show you that one because that one's a bit too complicated. So we're again invoking a variety of tactics, and we're using sledgehammer and so on. But ultimately, this is the property that we want to be able to prove. And so we define two functions, imps and outs. And what this does is so Circus is based on trace semantics. So what this does is, so these two functions take tracers and extract from them the input events and the output events, respectively. Right, so you have a list of events that are happening. So inputs and outputs are interleaved with each other depending on what you're interacting with the buffer. And then the property that we want to prove here, P1, is that so we have these three parts. So this is our pericondition. And what this is saying is that in every quiescent phase of the process, the set of outputs which have been given is a prefix of the inputs. Now, what does this mean? Well, it means that everything that I put into the buffer must eventually, well, not must eventually come out, but if I extract outputs from the buffer, then that list of outputs must be a prefix of the inputs that I put into the buffer first. Right, so this is a property that we can verify. And essentially this is automatable, so we have another tactic called RDES-refine, which allows us to discharge these kind of refinement conjectures. It's not quite as automated as Hoare Auto, but ultimately we can prove it. This property using this tactic, again by this interaction of axiomatic semantics and sledgehammer to discharge our proof obligations on the other hand. So that's one property that we can prove, and then the last property that we prove is that our buffer is deadlock free. So we have a specification called CDF, which I won't show you, but essentially CDF is telling us that in every quiescent state, so in every state where we are waiting for interaction, at least one event is enabled. So whenever I stop, I'm always allowing at least one event to happen, and that's the meaning of not deadlocking, right? Because there's always an event that can happen no matter what state I end up in. And so we say the buffer refines CDF, we unfold its definition, we apply this tactic RDES-refine plus sledgehammer, and we can prove our goal, right? So then going back to the example I showed you with RoboChart, essentially what happens internally is you take that syntax of state machines, you compile it into this kind of reactive program specification, and then you apply these same tactics to reason about it, basically. So we can now reason about infinite state systems. So you can kind of think of this as like an infinite state model checker somehow. So if you can write down your property in this way, then we can check a reactive program satisfies it. Of course, there's a bit more work to be done there for us. I mean, we need to have a decent property language, which we don't at the moment. But hopefully this illustrates the breadth of what you can do with this approach, right? I haven't gone into hybrid systems in more detail, but as I've said, you can deal with continuous dynamics. Isabelle has this excellent implementation of analysis. So I think that's really all that I'd like to say in this tutorial. So if you're interested in more, there's quite a number of publications that we've written about this. There's more tutorial material available online, and of course you're more than happy to talk to any of you about this work in more detail. But yeah, otherwise, thank you everyone for coming, and we'll finish that. I'm happy to take any questions just by way of conclusion.